you in the technical management of this webinar. So, and you will see we have several people from Act and Match which are connected and who will be there to help you throughout the event. So before I give the floor to our speakers, I will just give you some information about the interface. The point is that for you to be familiar with it and to know how to have the best experience. So the first thing you need to know is that you have the possibility to move the AV pod a little bit to your to the right of the interface. It will free the space in the center where you will have the presentation. So you need to click on that final here icon in order to move the AV pod on the right. Then you will have a possibility either to raise a comment or to ask a question. The difference is that if you click on the question mark before you send your message, it will be considered as a question, technical question by the system, and we will be able to promote the questions for you when it's the time for question and answers. If you have any issue or you want to raise a comment, you can use just the chat by itself without typing the question mark, and then it will be like a comment that will be in the chat and you can use it, and please use it as much as you want and let us know if everything is okay for you. You can translate the interface into English or your language if you prefer. You have this here world map, and it's written Français, but you can click on it and get your different languages if you want. You can also translate the chat into English if you want. If there is any message which is not sent in English, you can use this chat parameter wheel in order to do that. So please let us know if anything is not clear, and we will welcome Sylvie Escribano for the introduction. So Sylvie, whenever you want, you can activate camera, microphone, and I will put the slide for you. Have a great webinar.
Okay. So, thank you, Marine. I would like to start by, well, thanking Act and Match for the overall organization of this event as a webinar. And I hope that we will have soon the opportunity to organize this kind of event face-to-face. So, well, good morning, everyone. And on behalf of the Hydrate Consortium, it is my pleasure to welcome you to this final event or final workshop of the project Hydrate. So I hope this will be an interesting platform for you all to discuss about hydrogen quality and the impact on the proton exchange membrane fuel cells. Let me show you the agenda of the day. So first presentation about the project will be given by Jana Vitakangas, who is the coordinator from VTT of this project. Then we will have a first session about the outcomes of the project on PM fuel cell impurity measurements. We will start with presentation by several authors, several groups on the reversible impurities, namely carbon monoxide and its impact in automotive conditions. Then after the break, we will have two presentations about non-reversible impurities, or what we call here other impurities, starting with a talk by Uli Miss on the impact of hydrogen sulfide, and then a common talk with main presenter Thor Arog of SINTEF about new impurities, halogenates, freon, toluene. And then the afternoon session after our lunch break will be about the outcomes on the sampling and hydrogen purity assessment. 2 talks will be given by Tor about hydrogen refueling station fuel quality assessment and about online analysis. And then the last talk about hydrate results will be given commonly by Thomas Bacard and co-workers on the 3 laboratories able to analyze the contaminants regarding the current standard for hydrogen quality. And we will have the pleasure to listen this invited talk given by Idenori Tomioka-san about the ISO TC197 activities, so the standardization regarding fuel quality, hydrogen quality. And the day will end by some conclusions about the activities of Hydrate by work package leaders, and a discussion will be led at this moment by Alex Kabza from ZSW. And I forgot to say that after the different presentations, we have still time for some questions and discussions along the day. Well, thank you very much, and I wish you a very good workshop. Jana will now present the project.
Thank you, Sylvie. And thank you all for joining for today's event. This is the last event for the Hydrate project. Naturally, we would have wished being able to meet in person at the end of the project. However, this is or was not yet the option available. So I'm Jaana Viitakangas from VTT Technical Research Center of Finland. I'm the coordinator of Hydrate project. Before we go into the presentations, the results we wish to show you today, let's have a brief look what Hydrate project is about in overall. So Hydrate project was started 2018, funded by FGHAU, a 3-year project which then had an extension of 9 months. Therefore, this month we are now is the final month of the project. We have 6 fuel cell research centers as a partners and 1 independent European automotive stack manufacturer. The overall objective has been and is to solve the hydrogen quality for transportation applications. We have been studying the effects of the hydrogen supply chain delivered contaminants on the fuel cell automotive applications, on the fuel cell systems, fuel cell stacks, especially. We have been gathering technical data on fuel composition from the hydrogen refueling stations within Europe, where there is still not much information available publicly. Within Hydrate, also 3 European laboratories have been established who are capable of measuring all of the contaminants according to the ISO 14687 standard. Within Hydrate, we could say we have had 4 main topics. One big part of the overall project has been the fuel cell impurity measurements that we will now first talk about in the morning. We have had hydrogen fuel quality monitoring at the hydrogen refueling stations as another topic. A third big part of the project has been establishing the purity laboratories within the Europe, 3 hydrogen quality laboratories. And then we have also been studying the hydrogen supply chain contamination risk mitigation. Then I would like to propose to continue directly with the technical presentation themselves, where I will be continuing with you talking about first the impact of the carbon monoxide in automotive conditions. So this work, the presentation is a little bit longer presentation. This work has been done not only by us here at VTT, but 5 different partners. So as in addition to VTT, CA, SINTEF, ZSW, and NPL. For the most part, I will be talking through the presentation today for you, and the latter part will then be given by lovely Sylvie from CA. The overview of the presentation is that first we take a look at the background, methodology, and measurement procedures part. This has been the same throughout the overall project, and there are more comprehensive presentations also available about these already on our website. But we have a look and remind ourselves why this activity was initiated, why and how it was conducted, before we then venture into the measurements and the measurement results themselves. About the measurements, we take a look at the CO reference measurements. We take a look at the poisoning with CO and CO2 mixtures together. Then we have a look the isotopic CO measurements, so carbon-13 labeled CO for the studying of the effect of course CO poisoning, and in addition the internal air bleed effect on it. Then we also hear about the impact of CO with the fuel cell dynamic load cycle procedures given by Sylvie, and then finally also briefly about the comparison of the results with S2 and S3 stacks, which are slightly different due to the conditions and the cell areas. So we are able to have higher current densities with the S3s, also due to the slightly higher operation pressures. The measurements we present here you today, some of them, there's a large set of measurements being presented, and some of them have been run very recently. Therefore, we will give you the first outcomes, the first conclusions. However, the more comprehensive conclusions is yet to be made, since there is still some data treatment ongoing as we speak. Background and methodology. The overall objective, of course, of this work was to provide the recommendations for the ISO standards 14687, namely the hydrogen fuel standard for the automotive applications. And also to develop recommendations how to conduct fuel cell contaminant measurements at the stack level in automotive type operation. Automotive hydrogen quality, as mentioned, is of course set at the ISO standard 14687. Here in Europe, we look more closely to EN 17124 standard. However, these go very well hand in hand, and the overall standardization work is naturally worldwide in the topic of the hydrogen fuel quality. And the approach we have taken is that since still in the current version of the standards, and the limits for the impurities are largely based on measurements with single cell studies, and this may not be the best representation of automotive stacks and automotive conditions. Therefore, we have been conducting measurements with short stacks, and particularly we have taken the fuel recirculation into this system in order to consider the accumulation of impurities of different kind of species and the gas permeation through the membrane also in count. The anode recirculation is considered to be most representative for the fuel cell impurity measurements because it's more close to the real application, and as said, the accumulation of the impurities and other species is possible within the measurements. Another very important topic here is the permeation of the gases, especially the permeation of the oxygen have an important role for the carbon monoxide oxidation, as has been shown in literature. So while we have the recirculation, we have the oxygen recirculated within the loop as in a real system, and we are also able to avoid extra oxygen coming, for example, in some cases from the humidifiers used for the fuel humidification within the test benches. In addition to oxygen, realistic amounts of CO2 is also seen, because even when we don't have the CO2 in hydrogen, we always have it within the system, within the anode fuel gas, as it permeates through the membrane from cathode to the anode. And a third issue to be mentioned, that when we have anode recirculation system, it is much easier to apply gas sampling, online gas analysis within the measurements, since we have sufficient flows and we do not interfere too much with the actual operation of the fuel cell, even though we have a slight extra circulation to the gas sampling equipment or gas analysis equipment, or sometimes also a small bleed due to the analysis equipment consumption. Then taking a look why CO and CO2 are being studied within the project. The original reason for CO was that when this project was applied, there had been proposed to make a further reduction in the CO limit for the ISO standard. So from the current 0.2 parts per million to 50 ppb. Naturally, we all understand that making more tight limits in the standard fuel standard will have an additional cost, and the current situation is that we would preferably like to have reductions in the cost instead of getting new costs added into the hydrogen fuel to be more consumer friendly. Therefore, further evidence was needed, and it was needed in the fuel cell automotive application operation conditions. Carbon dioxide is a species that, as mentioned, is always present in the fuel recirculation loop, even if not present in the fuel itself, but due to the gas permeation, we have CO2 always present, and with high fuel utilizations, the concentrations can be notably high. There has been evidence in the literature that significant formation of CO from CO2 is possible, and therefore this, even if itself is not poisonous to the cell, but is contributing to the poisoning of the cell through the formation of CO. Measurement procedures. When the project was started, there was any recommendations for stack level measurements with anode fuel recirculation, especially for the impurity studies, but in general for any kind of fuel cell studies available. The basis for the procedures and protocols used in the project are the GRC's EU harmonized test protocol for MEA testing, that is in single cell operation, and then also the recommendations found from the FGHAU project stack test, which are also available publicly and can be found from the web. We have, for the CO and CO plus CO2 measurements, we have 5 partners who have been participating in these studies. We have 5 stacks, 5 similar stacks from PowerCell, 10 cell S2 stacks with pure platinum catalyst, low anode loading, cathode loading, membrane thickness are state-of-the-art automotive type, not disclosed in this context. All partners have suitable sized, quite similar test benches available at their site within which these tests have been conducted, all equipped with fuel recirculation loop. The stacks that were used for these studies were circulated among the partners, so more than one partner measured with one stack. Similar program was utilized for all of them. The conditions chosen were 70 degrees, 70 degrees relative humidity, 60% at the 70 degrees, slight pressurization at the anode and cathode, 130, 120 kilopascals absolute shown here, being measured from the outlet of anode and cathode, and with the air stoichiometry 2 and hydrogen stoichiometry 1.0 0.01, naturally referring to the overall stoichiometry and not per pass stoichiometry of the fuel. The measurement sets were such that the first day and the last day of each of the measurement campaign were conducted similarly, starting with startup, braking procedures, and then polarization curve and a reference poisoning measurement with 5 ppm CO before shutdown. In between, we had the impurity measurements conducted depending on the stack and partner. Different concentrations of CO were used from 0.5 ppm to 2 ppm CO, in addition to a few measurements with 0.8 ppm CO plus 2 or 20 ppm CO2. Reference days. As mentioned, we had detailed procedures for the startup. Quickly speaking, flushing with nitrogen, both anode and cathode, warming up the stack slightly up to 45 degrees, and then starting to draw current and warming up until the temperatures were up at 70 degrees before then continuing with the measurements themselves. Reference days, we did some braking, meaning some switching between so-called minimum and maximum current densities or currents. Then continuing with the polarization curve with agreed measurement points up to 1.2 amps per square centimeter. Then continuing with CO reference test, reference test made with 5 ppm CO in clean hydrogen, starting from the measurements of the baseline voltages at nominal current density of 0.3, continuing then to feed in the poison and until average cell voltage drop of 50 millivolts was reached. And finalizing the reference day with a shutdown procedure also detailed. So flushing the anodes and cathodes with nitrogen once again, or first consuming the reactants, then flushing it with nitrogen, doing an air bleed on anode side to oxidize all the impurities, all the CO from the platinum catalyst sites, and then shutting down the overall system and quickly reflushing both sides with nitrogen. The measurements with impurities were conducted with fuel cell dynamic load cycle. The fuel cell dynamic load cycle initially found from the JRC's report. This is based on the new European drive cycle. It could be argued to be slightly not up to date anymore. However, this is widely recognized, known, and yet the better cycle procedure to be made. So here in this cycle, quickly speaking, there are 4 so-called urban cycles with low powers, low current densities, and ending with high power extra urban drive cycle. And this was repeated throughout the measurement time. This was scaled to the maximum current set by the consortium, and the measurements were initiated so that a couple of reference cycles were first run with pure hydrogen, and then it was switched to the contamination at the level as agreed for that day, and continued until once again 50 millivolt drop was reached at the maximum current density point, or then maximum amount of cycles was reached. Now then, switching to the reference measurements and the measurements themselves. So reference measurements, why did we conduct this? It is seen that this kind of reference poisoning measurements with a known familiar poison, of which you have quite a lot of data available, you can determine the state of the health of the stack throughout its lifetime. Naturally, it might not be the best metrics to fully to be used to with different stacks, but at least with one certain stack you can see how its state of the health develops throughout the lifetime of your measurements. Naturally, CO poisoning, or in our case, in our reference measurements, the time that it takes the poison up to 50 millivolts is dependent on the state of the catalyst layer. The catalyst layer will degrade within the lifetime. There might be some agglomeration, some other oxidation, or some other species get stuck on the catalyst sites, and therefore the overall amount of CO that can absorb before the large performance drop will decrease, or will reduce the time it takes over the lifetime. What were the interesting questions in our case? Of course, that how reproducible the measurement is, both at one partner, with different stacks, at one partner with the same stack, and also between partners where we have similar but yet not exactly the same measurement equipment, the test benches. The protocol, as was briefly discussed already, is so that we start with pure hydrogen at the 0.3 amps per square centimeter load point, after which we switch to the 5 ppm CO poisoning, and this is continued until the 50 millivolt drop of average cell voltages is reached, or in some cases until the maximum time decided is reached. Cleaning after the day, the cleaning of the platinum catalyst is done by introducing air to the anode. during the shutdown procedure chosen. The key metrics that we have been looking is, of course, the time that it takes for the 50 millivolt drop. In addition, time it takes to the 10 millivolt drop, and between 10 and 50, as in many cases, the time that it takes for the first 10 millivolt drop might not be representative, as due to many things we might start the feeding of the poison at different state of the catalyst layer. Many small things can lead to this. So how reproducible is the poisoning measurement? Here we have one example run, or actually a figure of 3 example runs, which show very good reproducibility within one partner. So there's a small deviation. However, according to this result, there's yet not to be made any conclusions how is the reproducibility between partners. Then looking the different partners, we see quite wide of variation of curves, poisoning curves. Of course, trends is what we have been looking for. So far, we cannot be very conclusive. We can see some trends, especially within the same partner. So meaning that the state of the health of the stack is better in the beginning of the measurements than in the end of the measurements. However, there can be quite large differences between partners in this, and in addition, stacks were not all run similarly, so we do not have exactly the same data from each of the stack. Due to the time, we have to go slightly quicker through the measurements. So conclusions so far, what we have seen, what we have experienced, the CO tolerance can be a powerful tool for the state of the health. Reproducibility within one partner, within one equipment is very good. However, the reproducibility between different partners and different stacks can be varying, and it's yet to be further discussed where these differences might arise. Then CO was also measurements were conducted with CO plus CO2 mixture. Here, with the initial results we have, the fuel cell dynamic load cycle was scaled so that the maximum current density within the load cycle was 0.9 amps per square centimeter, due to the performance of the stack at that point. A set of measurements was made starting from 0.8 ppm CO and then adding to 0.8 ppm CO also 2 ppm CO2, and then also raising the CO2 content to 20 ppm with the 0.8 ppm CO. The trend that can be seen is that the CO2 appears to add the degradation rate. However, the differences here are not very large, and this still needs further investigation how the poisoning proceeds and how large the differences are when the CO2 is added into the system in addition to CO. And then still few words about CO measurements with isotopic labeled carbon, so carbon 13, for further understanding the behavior of CO poisoning, especially the effect of internal air bleed to the poisoning process. Monitoring CO behavior at the anode is challenging during the measurement. As we know, we can easily measure the CO2 coming out or the CO2 levels within the recirculation loop. However, this does not translate directly into the amount of CO2 that has been oxidized from the platinum catalyst site, because there is a quite large crossover of CO2 and other gases from air from the cathode to the anode. Some measurements have been conducted with CO2-free air. So this is a mitigation to the problem that most of the CO2 that is within the anode recirculation is actually the CO2 coming from the air from the cathode and not the CO2 that is being oxidized from the catalyst. However, when we are using the stacks, when we are measuring impurity measurements with stacks, it is rather challenging to run these kind of with these kind of large volumes of CO2-free air. Then isotopic labeling of CO, so using isotopic carbon 13 CO eases this problem. So the CO2 that is being oxidized from the anode, from the catalyst side, is easily can be easily measured and distinguished from carbon dioxide 12, which is the majority of carbon dioxide within the air, 99%, I think. And then mass balance can be made, and the oxidation rate during the measurements and oxidation rate during different conditions can be calculated. Here is a piping and instrumentation diagram from the single cell measurements. So the measurements were started first with single cell simply due to the simplicity to speed up the process. This is a publication already available for you where a single cell study was made, a poisoning measurement was made with 13 carbon-13 CO. The mass balance was calculated. So carbon-13 CO plus CO2 in and out, and the so-called missing CO was then concluded to be absorbed on the catalyst surface. And with this information, the surface coverage could be correlated with the carbon monoxide induced performance loss to the cell. In the same study, the effect of operation conditions was also studied. Here the cathode air pressure was changed during the measurement, which naturally leads to more oxygen permeating through the membrane to the anode, and therefore changing the oxidation rate of the CO on the catalyst surface to CO2 that can be measured from the circulation. Recently, the same measurements are being or have been conducted also with short stacks, now that the methodology had been shown to function on a single cell level. So the 10 cell S2 stack have been used within the test station with fuel recirculation and with high fuel utilization. Here, SIFT-MS and GC were used for the online gas analysis for CO2 with carbon-13 and with the overall CO2 and CO within the circulation. Preliminary results are shown here. However, the overall data treatment and the conclusions are being made at the very moment. So what is shown here basically is that it is replicable to the stack level measurement, and the same methodology can be applied on stack level. Similar to the single cell studies, also the operation condition variation was conducted on stack level. So here also the cathode air pressures were variated, and some differences in the concentration of 13 carbon labeled CO2 was measured. Now then, I think I have used plenty of time, and we have to give some time to lovely Sylvie as well. During my presentation, I have not been able to follow the conversation on the chat. I see there are some questions. However, I would like to propose that we take Sylvie on the stage first before we go these, due to the schedule, if that is okay for you. And in case we forget or lack of time to go through some of the discussions, as Sylvie mentioned, there is also reserved some time for discussions, further discussions at the end of the day. Okay, thank you.
Thank you very much, Jana. Who is our next speaker? please take the floor.
Okay. I am the next,
Okay.
the second part of this presentation. Okay. I can't find it. Sorry that I can't find the presentation in the list.
Sylvie, or
Sorry?
is it the one that I just put on?
Okay. No. No.
Okay.
This is not this one.
No, so that's...
I don't see it in the list, so I don't know where it is.
Anaël, can you promote the presentation of Sylvie?
Going to do it.
It looks like it has been removed from the list of presentations. Was called CO data stack S2 and S3.
Okay, so it's coming. Sorry for that.
It's
Oh,
okay.
it's here. Is it
Yeah,
this one?
looks like that.
Perfect.
Thank you.
Thank you, Anaël.
Okay. So fine, thanks. Well, I have to say thank you, lovely Jana, for your talk and your introduction. So this, I go directly to this one. This is a talk in two parts. First is about the effect of carbon monoxide concentration on one type of stack, and then the comparison on two different stacks. And here are the names of my colleagues at CA who helped a lot, of course, for all these activities and the work conducted in hydrate at CA. So for this first part of the presentation, dealing with the test of the impact of carbon monoxide during fuel cell dynamic load cycles, I will show results with mainly 0.5 and 0.8 ppm of CO. I will not remind the methodology and the protocols presented by Jana. So the experimental conditions, the tests have been conducted with power cell stack S2 type, which is 191 centimeters square, 10 cells. I don't know why I put here 192. So nominal operating conditions proposed or decided within hydrate have been used. So the 70 degrees C, the pressure 1.2 bars, stoichiometry 2, and well, that was presented by Jana. Also for the hydrogen, the pressure is 1.3 bar fixed. We are using recirculation and purges. This has been adapted to for our test bench for the use of this stack, and we are using flow limiters when possible. And here we have some tests showing the impact of gas feeding conditions, because it was also used for us to install or to develop the experiments. So the overall test program presented here. So we started with the reference test to check the performance on the pure hydrogen with IV curves and to check the CO tolerance with 5 ppm. In this case, we did some cyclic voltammetry experiments. Then we have a first series of contamination, so daily poisoning tests under load cycles. We repeated experiments for 0.5 and 0.8 ppm CO. We have one test with pure hydrogen also, and some impact of conditions that we show. Then we ended this campaign with the reference test, but it was decided to redo a short campaign to repeat again the 0.5 ppm. So these things are discussed within the project meetings to define this second series of experiments. And we ended with the reference test, the real end of test in this case. So sorry for this slide, which is frightening. I go directly to this. I try to explain. So the idea is that to analyze the data during the or after the fuel cell dynamic load cycles, we have different ways. And in this case, for example, we try to collect all the data for different levels of current density, different percentage of total load. So in this case here, what you can see is the different cell voltage, average cell voltages for all the cycles. So one experiment is about 20 cycles. First cycles are conducted under pure hydrogen. So here we can compare the voltage at the cycle 3 and the voltages at the cycle 20 at the end. So at the end of the daily test. And this was done for different loads. Here I reported only 2 cases. First slide is at low load, okay. So it's about 42%, I think, of the maximum current. And the reasons here are showing this variation, this decrease in voltage in millivolts. And well, for this particular first experiment, of course, we can see that one test in blue here was conducted under pure hydrogen. So in our case, in fact, it appeared that at this for this current, the voltage losses were about a few millivolts, and similar for pure hydrogen and for CO context, or 0.5. In this case, because well, we were, as I said, checking the experiments conditions, we have, for example, a difference in air pressure in one case, and this could not lead to a real difference in performance behavior and results. So this is for 0.5 ppm, and then we can see here the reasons for the 0.8 ppm case with 2 additional experiments, including flow limiters on the fuel line, with the aim to better control the fuel utilization and to increase the fuel utilization. So this was clearly noticeable and evident on the fuel, that this has an impact, and this also showed an impact on the accumulation within the recirculation loop, and the accumulation, for example, of gases coming from the cathode side, and best evidence was observed measuring the nitrogen, which gives a very good information about the the real accumulation we get there. And also for us, it is a good way to check that we are in conditions good for fuel utilizations and representative of a system when the nitrogen accumulation reaches several % in the hydrogen loop. Okay, so what we can see here is that we have slightly lower voltage and higher losses with 0.8 ppm versus 0.5 ppm. But in addition, we did not see strong effect of the fuel feeding or even air feeding conditions. So I spent some time on this one, and then the next one is the same thing, but at higher load. So it was here, in this case, it was 100% of the load used during the FCDLCs. So what can be seen is that we have an increase in the voltage losses from first cycle 3 to cycle 20. Again, we can see that with pure hydrogen, it is here slightly lower, but it is the same range. And again, the losses with 0.8 ppm are much higher. So there is a clear impact here. So in general, there is more impact at higher current density. And there are higher differences in the voltage losses between experiments and also between the different CO contents. So fuel feeding also shows more impact in this case. Maybe you can see here in blue and green that probably the performance are lower. Then there is here also a difference in performance caused by some pressure impact. But regarding the contamination and the losses, it is different for all these conditions. So then let's go to next slides, which in fact give you a different way to analyze the data of these same experiments. And here we are calculating the degradation rates during one day. So these degradation rates are assessed for each level of current density. So we get slightly more information with the degradation rates in volt per hour versus the different current density used during the selected current densities used during the FCDRCs. The results here, all this, or more or less yellow-orange curves corresponds to 0.5 ppm for the first series of tests. The blue one is for hydrogen. So this is what I said before. No real difference. So there is a slight daily degradation also under pure hydrogen. And in this case, we are not using a limiter on the flow. So we can assume, we observe that there is no accumulation within the loop from the permeation of the cathode excess gases. On the right side, you have the first series of tests conducted after these ones with 0.8 ppm. So we again, there is a repetition in this case of 5 times. In general, the degradation rates are always higher versus 0.5 ppm. In this case, it is not clarified who's who, but there is a comparison of experiments without and with limiters on the purges. And we can see no difference despite a strong nitrogen accumulation in one case, I mean the case with limiter. And also, even if not really measurable in our experiments, there could be some accumulation of other gases from the cathode side or from the anode side, which could have an impact, but not visible here. Okay. Oops, sorry. So then on the left, you have exactly the same figure. On the right side, sorry, this is the second series of tests conducted some weeks after the first series. Again with 0.5 ppm, and because we had this to check, wanted to check that, one test with 1 ppm. So there are 4 repetitions with exactly the same limiter conditions. And what we can observe, for example, is that we have the same dispersion in the results when comparing to the other sets of experiments, which were including also some variations on the conditions. And then the overall average losses are always below 0.8 ppm, shown before. But we have higher losses compared to the first series. So maybe there is a small loss in intolerance with time in this case. So about the impact of these experiments on on the performance and on the CO tolerance. Here are the polarization curves recorded here at beginning of test and end of test. So for the difference between beginning of test and end of test, it is light colors and darker colors. So you can see that the difference exists, but it's small. Here, this is the zero tolerance test conducted at 0.3 ampere per square centimeter. So the same colors. So blue is, you can check the blue. Blue colors is the mean value. So we can see there is mainly a slight decrease in performance. Well, a few, very small, few millivolts. But concerning the contamination, the behavior is always the same when considering the experiments reference tests at very beginning of test and after the first series. So we notice no impact of the test campaign on the dispersion, slightly more dispersion of voltage between cells than between than along the time. Sorry, I forgot to mention, that we are, of course, recording the voltages for all the cells, and this is the maximum and the minimum here. So this shows the dispersion between cells. And we have only low performance losses degradation caused by the test campaign, no decrease in CO tolerance after about 10 days cycles. This is consistent with an overall duration which is short, and the air cleaning procedure that is applied after each poisoning steps. Well, without deep data treatment here, sorry, I don't have the values for the active surface area in mind, but we did some CV measurements before and after the first test campaign. Well, at least on the left, you can see that all the cells have the same behavior and the same active areas on the cathode on the top and the anodes on the bottom. And here we can see in red the voltammograms after the experiments. So there is a negligible decrease in active surface area, which is consistent with what we observed on the data. And if a decrease, it could be slightly more on the cathode. And a link to explain the slight decrease in performance. Then I put here the polarization curves at the very end of the two series. So for the dark green curve here, you can see slightly more decrease, slightly more impact on stack performance after the additional series of poisoning tests. Well, however, these overall performance losses are still in the range of the cell's voltage dispersion. Okay, so these are some conclusions and about these experiments. So the major impact on daily performance losses are caused by the increase in CO concentration. So this seems obvious said like this, but well, we can mention that in our case, in this case, in these experiments, the clear effect could be seen only when CO is strictly higher than 0.5 ppm, because in some cases we could get similar data with pure hydrogen. And I say that this is the main impact because it was an unexpected low impact observed when changing the gas feeding conditions, considering the voltage losses, at least for these CO concentrations. For example, some variations on air pressure or variations in the fuel utilization when referring to the use of flow limiters or not. This had no impact on the contamination and degradation rates. And the trends are fully reproducible and consistent. Well, if some dispersion exists between experiments and between stacks, so these trends I'm talking about are also true for the other partners and other experiments conducted in the project. Then losses during the daily experiments are reversible for short-term campaigns. We noticed maybe some aging effect leading to higher sensitivity to both load cycles and CO. And this was caused by multiple FCDRC tests, even if those were conducted on a reduced overall testing time, I would say much less than 200 hours total. So this could be seen by comparing the two series and the 0.5 ppm. It's not mentioned here, but what can be missing from what we did is the impact of some contamination on the very long term, which is not really easy to manage, to handle. Okay, so now I will show same kind of results, maybe not explaining again the details, to compare S2 and S3 stacks. Okay. So for these experiments, we use the power cell stack S3. For those who are not aware of this, this stack was the one, or slightly the same as the one developed in the project Auto Stack Core. So it is 300 centimeters square. We had a special stack for us, a 4-cell stack, kindly made by PowerCell to be adapted to the specifications of our test bench. So the hydrate nominal conditions have been applied as far as possible, but adapted to the S3 design. It means that, for example, the pressures, we have different pressures depending on the current density. Stoichiometry air is 1.8. Okay, there is a difference between air and hydrogen pressure. And we are still using, of course, the recirculation and purges. For the test program, it is more simple, I would say. So always a reference test, the daily poisoning tests, 0.5, 0.8, and 1 ppm was tested. And reference test at the end. Okay, I'm sorry for that. I did not explain that. They will stop. The FCDRC load cycles have been modified, of course, because adapted to the design. So the maximum current now is 2 ampere per centimeter square instead of about 1. I hope they will stop that. For the reference test load profile, there are some changes compared to the S2 stack. So in general, the currents are higher, but we try to adapt in a way that the cell voltages are similar for the same steps of the test. And in this case, the zero tolerance test with 5 ppm CO is conducted at 0.5 amp per square centimeter. I have nothing else to say here. Okay. So an image to show that, well, we have indeed the same type of cycles compared to the S2 stacks. And again, we will check the voltage losses between cycles 3 and 20, and degradation rates for 18 cycles. Here comes the results. So first, the results with the 0.5 ppm CO. So on the left, the S3 stacks results. On the right, the S2 stack results. And similar to before, we are considering here the voltage at 42% of maximum current. As you can see, it does not correspond to the same current density, but a similar voltage range. I don't know if you can read it. Here we are about 710 and also 710 here. Well, this is the same scale. Okay, so what we can see is the average losses are 4 millivolts. 4.5 millivolts was obtained with the S2. If we calculate a degradation based on this value, it comes to 0.66 millivolt or 0.75 millivolt per hour. So we have similar differences in voltage at beginning of test and between tests. We have a similar impact at same percentage of load versus maximum. And in fact, because we are also operating at same voltage here. Then same results, but at maximum current, 600 amperes or 200 ampere per centimeter square in this case, compared to the 0.9 ampere per centimeter square in the other case. So what can be seen in this case, it was not possible to go higher. So the voltage range is similar, but not the same. Here it is 560, while here you have the 540, for example. So not exactly the same voltage. On the average, we are losing less millivolts, 7 millivolts. So there are similar differences in voltage again. So always a dispersion, but a lower impact observed with the S3 stack, which is operating at slightly higher voltage on this load level. Now I am going through these degradation rates versus the current density. So this is just the example of 4 tests for 0.5 ppm CO, just to show you the dispersion, because in the slides after this one, I am using the average of the values to easy visualization of the results. Okay, so this sort of yellow is used for 0.5 ppm CO. Purple is used for 0.8 and red is used for 1 ppm CO. So again, on the left, S3 stack, on the right, S2 stack. I also reported here the voltage. This is the mean cell voltage for the cycle 3 at the beginning of the test, and the mean voltage at the end of the cycles. So what can be seen, at least, is the trends are fully comparable regarding the CO concentration. Okay, I forgot to mention that again, the scales here are the same. So we are between 0 and 0.01 volt per hour. So the lower losses, and we observe lower losses and lower degradation rates during this daily operation. And here comes the reference tests applied also on these stacks at the beginning of test and the end of test. On the top of the slide, you have the polarization curves and the voltage loss during the zero tolerance test, the mean values. Well, in this case, it appeared that we have a slightly increase in overall performance. We can also notice rapidly that the contamination behavior with 5 ppm is not really changing. Maybe slightly higher because we have a slightly higher decrease, but this should be confirmed. And on the bottom of the slide, what I put is on the left, the polarization curves, in fact, for all the cells, because it was only 4 cells. And what can be seen here is that we have 2 cells that were presenting at the beginning of test lower performance, and these 2 cells showed a slight improvement during the overall experiment. So this is why we have this improvement. Nothing to do with the CO contamination here. And here I only let the maximum and minimum values for the CO tolerance test. to show that the maximum are joining, in fact, at the end. Okay, if we try to give an overview or some conclusions about this. So first of all, the operating conditions were adapted to the design or to the higher power density of this stack, and this should be done because, stacks are supposed to be operated in the nominal conditions to give valuable data. So not exactly the same conditions when comparing two stacks. At least we operated to get similar voltage levels during the contamination steps, if not same current densities. We clearly observe same trends as with the stack S2 regarding CO concentration effect in the range studied here. We confirm the impact on daily performance losses, which is caused by the increase in CO concentration in the range 0.5 1 ppm, with much more impact when going higher than 0.5. In this case, we had an improved performance after this campaign. Possibly not sufficient break-in was considered for explaining this. Then we have a lower sensitivity to load cycles and to CO contamination. This should be still clarified. There could be differences in membrane electrode assemblies or in local operating conditions induced by the operating features that would explain this. That would explain this, but for the moment we don't have the reasons enabling or the information enabling to conclude on that. And tests should be repeated by other partner, normally at VTT. And wow, now that's it for me. So we can probably get some questions. I'll try to answer some questions. I mean, not only Jana and myself, but the colleagues who were also involved can help answering questions. Okay, Marine or Anaël,
Yes.
do you want to
Yes.
lead the discussion?
Yes. So we're gonna respond maybe for the first question, which was in the chat. So will there be anything on ammonia impact?
Yeah, sorry, I answered this one in the chat. Ammonia was not tested in the project, as far as I know. Jana, if you want to put also your microphone on. Yeah. Not sorry not for the second one. 0.2. Yes, for a question of Martin. At least at CA, we did not this kind of experiments, but some people did this 0.2 experiments. I don't know, Jana, if you have better information to give on the 0.2.
Yes, well, initially the measurement set did include 0.2 as well as actually 0.05, so 50 ppb. But when the measurements were started and it was seen that not plenty of information was gained with that low amount of CO, so it was considered that it wasn't effective working to go on with a full measurement plan with so low levels of CO. So instead it was adjusted slightly, and there has been few measurements with 0.2 ppm. However, unfortunately, full data treatment and analysis is still on the way, and therefore this was not widely discussed on today's presentations yet.
Yes, and I at least remember the reasons obtained by SINTEF. I don't remember for the DSW, but there was an impact. I mean, the trend was also visible. If the stack is less tolerant, some were more or less tolerant. It is clear that there was an impact of 0.2 ppm, well, largely smaller than 0.5 and 0.8, but it could be measured. All the stacks did not present exactly the same tolerance. Yeah, next question, probably.
Well, this one, thank you, Graham. I think you started already conversation on the chat. Very good. I guess we could admit here that we did have some issues with the MEAs. So we know that there is some issue with the MEA performance, the MEAs that we were using. We are assuming this to be largely to do with the fact that we did make a choice of using pure platinum catalyst instead of platinum with additives, which would actually be the state of the art for the MEAs. The choice was made in order to be able to have the information about what is actually on the what is the catalyst, what there is at the catalyst layer. However, we also noticed that even if we know the catalyst, even if we know the exact loading of the catalyst, what is more important is the particle size, which affects greatly to the catalyst area more than the loading itself, and there can be very large variations in that, even if the loading is the same. We also had the pure platinum catalysts in preceding high Cora project, so we saw that there would be some additional value that we could compare the gain data with the former data we have already as well. About the issues with the MEAs, well, we see that the choice we made with the pure platinum has most probably affected that we didn't have the commercially utilized MEAs. So we had MEAs that were made in small batches, and unfortunately, if you order small batches of even with a slight differences with what is produced in large amounts, then of course it's more manual work, and this exactly might be the result. So, so yes, yes, there is a difference.
Yes, and as you say, Aline, the S3 stacks results are showing good performance, and it's also interesting to show that these stacks are showing also the same trends regarding the contamination. So they are less contaminated, but the link can be done.
And the effect, the performance was especially poor, if we say it that way, notably worse at high current densities with the MEAs that we used. You may then ask, why didn't we just replace the MEAs with the good ones? Well, the possibility to order new ones and get also a wide variation of quality was, we considered that it was evident. So we saw that there is still additional value, even though it can be seen that the performance at the higher currents is not actually the state-of-the-art MEA performance.
Okay, thank you. So there is another question from Gabor.
This one I replied in writing. Do we want to repeat?
Yes, maybe for the person who didn't saw the question and the answers in the chat. I don't know. Or maybe we can switch to another question.
Yes, unless Gabor wants to state the question or make another comment or question, further question. Maybe this would be more interactive in that way as well.
Yes.
If my first reply wasn't sufficient.
Okay, so maybe Gabor, I'm gonna give you the access to your camera and your microphone, so you can interact with Jana and Sylvie.
And please, the rest of the group who are very much involved in this work as well.
Yes.
So Gabor, you can activate your camera and your microphone. It's the two icons that are red for now. You just have to click on it and it will be green.
Yeah, I guess it works.
Yes, perfect.
I guess the question is clear, isn't it?
Yeah, well, actually, I was also referring to the first one.
Yeah.
That was okay?
This is okay. I understand the reason.
Okay, yeah. Well, it seemed to us that it's not wildly enough investigated in case there is a pressure to put that lower, and it wasn't completely, the case was not disclosed if there was partially seen need to make it even lower, which would have been slightly problematic from the other point of views. And we didn't see that it was fully convincing that there is a clear need to go that path with the ISO limit of CO. So yes, it has been widely investigated, but not so much with the recirculation and the effect of the gas permeation, which is even more pronounced now when the MEAs has been going thinner in the recent years, which may not be the case with the setups that the most of the data had been run in earlier years.
But do you think that there is something new which was found out here?
Well, unfortunately, yes, the full conclusion is not shown here as it has not been made. So,
okay.
So I do wish that we have a better layout than to present in the written form as we finalize all the putting together all the data that we have.
Okay, thank you.
Thank you.
Just if I may, I mean, here we are also, there is a question about the comparison between the single cell and stacks. And then at a certain point, for the application, it cannot be possible to really ask for, yeah, this is the question. So I don't have the exact answer because we don't have single cell operating in the same way as with the stacks and with the same MEAs, with the same, well, in fact, this comparison, this exact comparison between a single cell using the same conditions and the same MEAs, we don't have it. So, as Jana said, we have to further treat the data and try to conclude on these aspects. But I fear that it is needed to have this test in real stacks to enable to propose or to recommend something on to the standard. Because at the end, a single cell, and particularly the small single cells, they give very good results and good trends, but not the final. It's not the final validation of what can be done or what can be expected from the contamination or not. So this was also a aim of this project: stack and recirculation, kind of real conditions. But okay, we still have to further check all the results obtained.
Thank you for that, the clarification for that. But maybe that's kind of the issue we need to take care. And so the original data for given into that ISO table, then it wasn't always a single cell test, the data from single cell test. So we just wondering if that's what is happening in that the real cow or the stack. So something other happens or any change between those testing. So then that is a very big question for us. So then if you
of course
can find that, if you can find something that this is that the point. So then it's going to be really good help for us for the future discussion. So that's why I'm just asking.
I fully understand the question. I guess that what should be checked now is the comparison between to go back maybe I don't know, to single cells with other operating conditions more representative and MEAs for the right maybe designs also corresponding to the right designs.
Maybe we can something that how it affect the degradation of the performance of the single fuel cell in the single cell test, and so we can validate if that our data or just the result specification number is good enough for that, and so we can evaluate that in the stack testing. So that is a way we are doing here. So just so anyway, it is really difficult to know how it will be. So anyway, thank you so much.
Thank you for the discussion.
Okay, thank you for your answers. So I think that the next speaker is Ulrich.
Okay. Can we propose a short break anyway?
Yes. Yes, we are going to do a short break. How many time do you want?
And it's strange that nobody can comment. It's okay if we go for 10 minutes?
I think that sounds good. I can comment.
Thank you.
Okay, perfect. So see you in 10 minutes for the next presentation.
Thank you.
Hi everyone, so we're back. I hope that you had a nice coffee break. So the next speaker is Ulrich. Can you please activate your camera and microphone?
Yes, welcome.
Hi.
Hi.
So here is your presentation.
Thank you.
You're welcome.
Okay. Then I will start. Welcome to my presentation regarding the work package 2.2 in Hydride project. The topic here is non-reversible contamination. So we have a closer look to hydrogen sulfate contamination, and in particular the recovery methods after contamination with sulfur. Okay, short outline of my presentation. I start to explain the focus of Work Package 2.2. Here's the ZBT part, followed by an overview of the measurement campaign. We investigated in the project 3 recovery strategies, started with the fuel cell dynamic load recovery, followed by long stop with defined start-stop procedures, and finally H2 soak measurement recovery. I closed my talk with a short conclusion of the measurements. Yeah, what was the motivation for the measurements in Work Package 2.2? Yeah, it's well known that sulfur impurities can get into the H2 chain by single events due to delivery or distribution, and also maybe from sealing materials like EPDM and so on. So accordingly, H2S can also enter the stack and the platinum catalyst. If sulfur stays in the platinum catalyst or the anode surface, the CO tolerance is seriously lowered. So the tests we performed in this work package are not focused on sulfur tolerance of the system or the stack. Rather, we wanted to evaluate the reduction in CO tolerance due to sulfur contamination. Yeah, as mentioned before, the focus is on recovery methods, so FCDSC start and long stop recovery, and also the H2 soak, so the contamination. Yeah, we contaminate the stack here with a quite high sulfur concentration level, so in a ppm range between 1 and 1.5 ppm, compared to the very, very low ISO 14687 concentration level of 4 ppb. So we contaminate the stack until an average voltage loss of 30 millivolt is reached. There were different tools here for analyzing the stack recovery processes. We heard before in the presentation, one very interesting tool is the CO reference poisoning here, again with 5 ppm in H2 until an average voltage loss of 50 millivolt is reached. And further tools for analyzing recovery processes are, for example, O2 measurements in the loop, the beginning and end of stack characterization, and yeah, it's well-known polarization curves. Okay, here first of all the test bench or the test setup at ZBT. Yeah, we integrate here a 10-cell power cell, the S2 stack mentioned before in the presentation, integrate a very compact, isolated and fully heated recirculation loop, included an active pump and a water separator. Yeah, we want to reach close to system operating conditions. A quite high H2 utilization, approximately in this experiment between 97 and 98%. Performing the standard FCDSC automotive cycle, and we have here no active humidification at the anode side. So we integrate gas analytic devices here in GC for measurement of the sulfur concentration level. And again, all procedures are based on the test procedures are based on the Hydride Work Package 2 documents we heard before in the presentations. Okay. For the sulfur measurements at ZBT, there were available 2 stacks. With the first stack, we perform the FCDSC recovery methods. So we start here with a contamination of 1.5 ppm H2S in H2, and then performing the part 1 measurement. So in total 25 FCDSC followed by prolonged FCDSC recovery strategy with in total 250 FCDSC, and finally a short one again with 40 FCDSC. And with the second stack, we contaminate with a quite lower concentration here, 1 ppm H2S in H2, performing the long start recovery, contaminate again with 1 ppm H2S in H2, and finally perform the H2 soak recovery. Okay, it's an overview of the first FCDSC test. In blue, the current density curve, and in red, the average stack voltage over time. All contamination processes are performed at a quite low constant current density of 0.3 amps per square centimeter. On the left side, we see the first CO poisoning before contaminating with H2S, followed by a short break and an air bleed to clean the catalyst. Then we contaminate the stack with 1.5 ppm H2S, followed by a polarization curve and again a CO poisoning. And then we perform the recovery loop, which at each loop 5 times FCDSC mode, followed by the CO poisoning and a short break, a short shutdown. Here you see the comparison of the CO reference poisoning. The voltage in percent over time is seen here. The first one, the red curve, is the CO reference poisoning before contamination with H2S, and the following curves are after the contamination with H2S. So we have here the trend of the recovery possibilities during our experiments. So what we see here, the red curve, a voltage loss of 50 millivolts could not be achieved within the first 2 hours. So, but what we see here is nevertheless after H2 contamination, we see a significantly more sensitive response to the CO poisoning after contamination. So which means a reduction of the active area of the stack on the anode side. And also it's mentioned here, we have only a very slight recovery due to the FCDSC recovery methods. We wondered about the very slow voltage drop before the first contamination. So for this reason, we evaluated the parallel performed oxygen measurements in the loop. Can be seen here, the curves of the oxygen concentration in the loop. So the y-axis represents the peak area of the measurements device. So the value of 20 area corresponds approximately to around about 20 ppm O2 in the recirculation loop. The blue curve here is the curve of the oxygen concentration during CO poisoning before the H2S contamination. So initially, a decrease in the amount of oxygen is observed in the recirculation loop due to the reaction between hydrogen and oxygen from cathode side on catalyst surface. So what we detected here is a minimum concentration around about after 30 minutes. The first strong degrees, we think one possible promoting reason for that is that we have here overlapping effects due to insufficient and nitrogen flushing of the test set up before starting the test. So we have a quite high oxygen concentration in the loop. Nevertheless, after the H2S contamination, an increase can be detected more quickly. So we have a faster O2 increase over time, which suggests a considerable reduction in the active catalytic surface. But by measuring the oxygen content in recirculation loop, what we see here is really no recovery of active surface can be detected due to the FCDSC cycling. So we have here not a very good recovery method seen here in the experiments. Okay, next slide was the next test was here to perform the prolonged FCDSC recovery test. So in total 250 cycles. The results of this test were nearly identical with the results before in terms of the trend. But what we've seen here is, or what we've seen in this experiment, is an increased degradation. And we think partly due to dry out effects during the FCDSC. So we have chosen operating conditions, the stack temperature, dew points at the cathode side, and a fixed minimum volume flow at 0.3 amps per square centimeter, resulted in a quite high stoichiometry during the low current densities at the FCDSC. And this operating conditions did not match stable operating in FCDSC mode over a longer time of the experiments. So in this case, we started to adjust the operating conditions for the following campaign. Thanks here to ZSW for the main work in this process. And you see here the comparison of polarization curve with the so far used conditions. So performing at 80 degrees stack temperature and a dew point of 64 Celsius. And the new data here, stack temperature decrease up to 70 degrees and a dew point of 60 degrees. So what we reached, or what we achieved here is with these adjusted conditions, is a higher performance. We have stable operating over a long time, and also now we see no dry out effects. So we adjusted test conditions for the second test campaign. Here is the recovery method. The next method of recovery was a start-stop long term. We see here the whole test in the diagram on the right side, and an overview of the test procedure. Only very short marked. Here's the procedure. We have the CO poisoning, contamination with H2S, again a CO poisoning, and a shutdown with an air purge, and then we start the loop here with the characterization, A times FCDSC, a shutdown, and then a long downtime time, a cool down of the whole test. So stack including the test setup for 12 hours. And then we start up again and perform a characterization curve. So here, a little bit zoomed into the beginning of the measurements. Again, the CO reference measurement, reference poisoning before contamination. It takes round about 88 minutes to get a voltage loss of 50 millivolts. And after the H2S contamination, we have again a significantly more sensitive response to CO. So we need only 38 minutes to get a voltage loss of 50 millivolts. The H2S contamination level, so voltage loss of 30 millivolts, lasted around about 160 minutes. It's very important to mention here that we get a first strong, we call it voltage recovery during the first polarization curve directly after the H2S contamination. You can see here the curve starting from high current down to OCV, and again up to the maximum current in this experiments. And we see here on the blue voltage curves, we see a strong degradation during the first 30 minutes of the polarization curve. A short look to the comparison of the CO reference poisoning of the long stop test experiments. So in wet, the CO poisoning time before the H2S contamination, around about 90 minutes. And in green, the poisoning time after H2S contamination. So very strong influence of CO around about 38 minutes. And after the 5 long stops, we see an increased time of the poisoning. So we see here a partly recovery due to the long stop test recovery methods. However, as mentioned before, we think the first strong voltage recovery occurs already during the first polarization curve before the long stop. Okay, the final test included H2 SORC procedures to see the recovery effects. Again, very short, the procedure here of the test. Again, CO poisoning, H2S contamination, and CO poisoning again. Then a shutdown, and then we are in the loop. Polarization curve again, 8 FCDSC, and then we perform an H2 SORC shutdown process and a very short downtime of only 30 minutes without cool down of the stack or the test setup. Yeah, the definition of H2 SORC can be seen at this slide. So we started with 2 short SORCs, can be seen on the left side in this slide. The conditions here are stack operation at ambient pressure on both anode and cathode side. And we stop the air supply and continue with an H2 supply for only 2 minutes. After that, we perform 3 long soaks. So in this case, with the overpressure on the anode side, and with a longer H2 supply of around about 7 minutes. We see here on the bottom the results of the CO poisoning. Again, the red one is the CO poisoning before contamination with H2S. The green one is after the second H2S contamination, and the blue one is after 5 H2 SORCs and short stops. What we see here is no recovery effect due to the H2 SORC. Quite the opposite. We see rather worse performance after the H2 SORC measurements. We don't know the exact answer or the reason for that. So we have to analyze this in more detail. As mentioned before, with the second stack, we have 2 times contamination with H2S. We see here the duration of contamination, a comparison. The first contamination with H2S lasted around about 160 minutes, and we see the second contamination with the same stack. So here we have a lower start voltage level and also a faster contamination level, only around about 120 minutes. So what we can see here, we have irreversible degradation after the first recovery test, the long stop test. We see a very strong influence on the second H2S contamination, so recovery seems to be not complete. It's no surprise regarding sulfur contamination. What is the conclusion of VP Work Package 2.2 at ZPT? We find out that the CO poisoning tool is a very effective method to evaluate the reduction of CO tolerances after H2S contamination. The best recovery method seems to be the long stop with a cool down strategy. In most cases, we also see that we get a higher voltage level after long stop operating. So there are very helpful processes to eliminate the reversible contamination. Yeah, nevertheless, a complete recovery could not be achieved. H2S leads to irreversible stack degradation with partly stronger voltage loss within short time. What is finally mentioned here, our tests provide no new information about limit values for the sulfur contamination regarding the ISO 14687. And furthermore, a deep insight into the contamination mechanisms could not be provided here. But I think we have some more information about the behavior of the stack within recirculation loop and the possibility to recover the stack after contamination with H2S. Yeah, thank you very much for your attention.
So thank you very much for your presentation. If you have any questions, you can ask them in the chat, and then, or if you want, you can maybe tell us if you want to interact with Ulrich, so we can activate your camera and your microphone to talk with him. Oh, there's a first question in the chat. So here it is.
Yeah, maybe some help again from my partners here. So we talk about anode air bleed for recovery in the testing protocol. How realistic is it? I think it depends on the strategy a little bit of the car or the transportation systems. The strategy is to avoid by all costs O2 in the anode side to minimize it. Yes, Eileen, we know each other a little bit, so thanks for your question, and maybe you give us the answer. So the use here for air bleed is to clean the catalyst after very high concentration level of CO or contamination with a very high CO level. So it has to be done because we want to see the effect of the recovery of after H2S contamination and not the influence of CO, as mentioned before in the presentation. So that's only to have the possibility to perform with a CO poisoning, reference poisoning. Okay, more questions? I don't know.
Some participants are writing their questions, I think.
Okay.
Okay, so I think that there's no more question.
Yeah. We will have some. I have to mention here we have some more information in the final report because we have some more partners in this work package, NPL and CEA. So we will have more information in the final report and more measurement from the partners.
Okay.
So this is Sylvie again here. Thank you for mentioning this, Uli. I do confirm at CA we started with preliminary experiments. Well, for the moment showing same ideas, but we do have to still to proceed to a more complete campaign of tests, and hopefully, if it works, we could get also analysis of H2S within the recirculation loop and see what happens during the contamination and during the recovery. But this was not feasible yet, so it's a hope, and clearly this will be put in the final reports about H2S. Thanks, Uli.
Okay, so thank you very much for your presentation and your answers.
Yeah, thank you.
So the next speaker is Tor. You can activate your camera and your microphone. Hello.
Hello. Yes, I believe that's the right presentation.
Okay, perfect.
Okay, so this is sort of a large presentation about a lot of the work on new impurities. I will along the way get some help from the lovely Sylvia Scribano and the even lovelier Christian Spitza, but I will start off with the outline. So Christian will talk a bit about the survey we did early in the project on new impurities, and then we will switch to the testing we have actually done. For halogens, we have been looking at several components, doing also fundamental half-cell tests and single-cell testing, also looking at some specifics on Freon. We also tested, we tried to test ionic liquid with several strategies, and also some results on organics and toluene. So I think we can start with Christian.
Okay, so everybody can hear me. Thanks, Tor, for kind introduction to the first part of this work, which was theoretical based, so a survey to identify critical components and maintenance practices at H3S, where the big focus was there to identify not only these components and maintenance practices, but to see whether there could be introduced some new contaminants to the hydrogen fuel. So as we know that the ISO 14687-2 considers just contaminants that are originated from the hydrogen production processes. And what we now just try to look at is if at the station there can be introduced new components, new impurities like from oil grades, lubricants, or others. So that was then the goal of this survey, where we then had certain activities to be performed. So we had first a questionnaire that we performed and did in cooperation with the German CEP. We did some literature surveys. We did interviews with component manufacturers, station operators and manufacturers. And also we incorporated results of the first OEM workshop from the HYDRAT project. So first coming then to what has been the results from the questionnaire. We just received a few feedback from 6 station operators and 2 tech providers. So as first information there, we did not get that much detailed information regarding maintenance practices or that then there some new impurity measurement has been done. What has been seen in this from these feedbacks that lubricants, solvents, and cleaning agents have been mentioned, like acetone, mobile, 10W40, Tramons, and steam clean, which are used at certain levels of manufacturing or maintenance of the stations. Also, what has been expressed is that ionic liquids residues with fluctuation concentration could be seen, but without further specification, which have been reported to us. Nevertheless, the purging of nitrogen and hydrogen is performed manually, mostly manually or partly manually after the maintenance work at the hydrogen lines. But afterwards, there's no quality check of the quality after these events. So this has to be recognized when we then look at the impurity levels and new impurities. Further results of the investigations that we did so far. So also these results were mainly from 2018. First looking at the HRS components, so all these sealing gaskets and compressors. So by sealing gaskets, there could be introduced some silicon And as we know, we had some events of oil compressors where we had some oil residues in the hydrogen stream. And as I mentioned before, also ionic liquid residues could be identified without further specification, as I mentioned, but at least we have some events being transported by these interviews that this had happened at some stations. Furthermore, particulates can be introduced by new stainless steel tubing, by valves, seals, and filters. And also from the polymeric coating could delaminate, leading to certain amount and constant and species to be introduced to the hydrogen stream. And as also mentioned before by Uli, that by the sealing we have sulfur species, as we have sulfur vulcanized FKM or EPDM with carbon black as filler. So these could lead then also to that sulfur could be introduced not only from the production process, but also from the station itself, which is quite important also when we will look at where to take the samples and where should be then the quality monitored at the station. Coming then more to the manufacturing and maintenance processes, as also in the standards is mentioned already, that from piping, from insufficient cleaning after manufacturing and maintenance, we have oxygen, nitrogen, and water contents being measured in some hydrogen samples. Also, particulates could be introduced due to insufficient cleaning after manufacturing. Further, by some lubricants, detergents in the pipings or in the maintenance and commissioning processes, we can find some sulfur and oil species. We have some surfactants, sodium, salt, acetone, and also freons that has been reported. And again, also disclosed already in the standards, incomplete flushing leads then to nitrogen, oxygen, and CO2 concentrations in the hydrogen stream. This then also for the maintenance, same here, these lubricant lead to oil or sulfur species in the hydrogen stream. And again, these resurgent detergents to surfactant, sodium, salt, and other species that could also be introduced. Same here again, for the lubricants, for new stainless steel tubes after cleaning, that could be introduced some sulfur components. So what are the results of this first survey, these first questionnaires? There are components like ionic surfactants, traces of oil, or non-ionic surfactants could accumulate in particle filters in a crystalline manner. So this is also to be that we should then afterwards have a look at the filters if we then can see some further species that have not been reported in the standards already. But what is a drawback here, that the probability of occurrence and concentrations of these potential new impurities is not possible to estimate it. So the risk thereof can be posed by such species cannot be assessed in a correct manner today. So this then led in this project to the requirements that we needed more analysis that Tor will show now from workpack 3 and 4. And as has been already been mentioned also by Tor, that we will show and disclose some impact analysis on stack levels from workpack 2. So that's the first part, and I will hand over again to Tor. Thank you.
Thank you, Christian. Okay, so then we go into some of the actual testing we did. So let's start with the Freon. So some of you know that this is something we've seen in samples over the years. And the thing that makes it interesting is that according to the ISO standard 14687, you would report this molecule on a hydrochloric acid basis, meaning that you would have to multiply the concentration by 4. So of course, then it would be interesting to see if the impact of the impurity is actually 4 times higher than that of hydrochloric acid. So the first thing we did was to sort of compare at the fundamental level using a platinum rotating disc electrode. And you can see here in the cyclical thermograms. The blue line is sort of the background. We use 0.5 molar sulfuric acid because it sort of emulates the membrane acidity. So that's the background signal, and then we added 0.51 and 2 ppm freon. And on the left plot, you see very little effect on these additions to the catalytic surface on the platinum hydrogen region and platinum oxygen regions. To the right, for comparison, we have added sulfuric acid. Hydrochloric acid, and you see the sulfuric acid background, and you see a clear effect in both regions on the addition. So clearly here, there's very little effect on freon on the RDE experiment here, whereas there's a clear effect on the hydrochloric acid. Looking at the oxygen reduction reaction, we can evaluate the current at a voltage of 0.8, and what you see here to the left then is the effect of freon. Not much difference, and to the right you can see that of hydrochloric acid. So if you use this bar chart to plot current density at 0.8, we see very little difference from the background for the freon at 0.51 and 2, whereas there's a clear effect on hydrochloric acid at 0.5 and 1. So then the question you would argue is, when you use a solid platinum catalyst, that could be pretty robust to poisoning, of course. So in order to sort of emulate what's going on in the fuel cell, we applied a platinum carbon coating. So we have about 50% platinum carbon loading onto the surface of the RDE. But then again, as you see in this plot, we did not see an effect of the freon, which is quite interesting. This is 1 ppm. So then we had a pretty comprehensive student work over the summer where we wanted to look at the effect of the freon on a single cell assembly. So what you see here in the chart is basically the baseline performance, and the blue line is the administration of 0.1 ppm freon, and the gray line is 1 ppm. So clearly visible is an effect of the 1 ppm. You also see that you would have a slight recovery after the poisoning of 1 ppm. Our goal here was to be able to evaluate freon at the 50 ppb tolerance limit of the ISO standard. But due to the inherent degradation of the cell assembly, we did not achieve this sensitivity to degradation for the single cell test. But clearly, in contrast to the half cell experiment, we did see an effect on single cell. So like I said, on the half cell, little or no effect of freon, but a clear effect on the single cell. So what we want to do is then further try to understand what's happening to the freon when it goes into the fuel cell. So so what you see here in this FTIR plot is that you can actually see at the beginning, because here we're monitoring the inlet freon concentration of 6.7 ppm, and then we switch to the outlet where we have a lot of water. So basically, the water is covering up the analytical signal, so it's really hard to see freon in gases with high relative humidity. There is a point here that we did not see hydrochloric acid in the spectra, and this region is not shown here, did not have an interference from water. So we're pretty clear that we cannot document any complete degradation or part degradation of the freon that would result in the production of hydrochloric acid. Yeah, this is EXA estimates for the testing of the single cell. You can see that the EXA change for 0.1 ppm was 7.7, and whereas for 1 ppm it was estimated to be 10.41. So the numbers, the changes are quite small. And then a big discussion in the ISO meetings has been how do we deal with the halogens as a group? Do we limit it to chlorine? What about bromine, iodine? So we wanted to do some testing of these species. So what we have done, I'll show some results in the next slide, is that we've tested and compared HI and HBr, and what we have seen is that the HI will completely deactivate the catalyst, so it has a strong effect. HCl and HBr are it has a similar effect in what we have seen. It affects the platinum oxygen region. And you can see it in the two plots here from literature. You see that the current here is much more retarded for HBr than the case for hydrochloric acid. So we believe that HBr has a stronger effect than hydrochloric acid, although we did not compare side by side. So that's why I put the paper in there that shows this work. Our work, what we did, you can see here on the left, again using platinum carbon surface on the rotating disc electrode. I have a typo here, I'm sorry about that. It should be HBr being much lower than HI. See if I can fix that. Yeah, so just to indicate, so what you see here is in blue is the baseline, and you see the red line is HBr, where you show a small effect, and then a almost full passivation of the surface with the HI. And also to the right, you can see the change in current levels at 0.8 that shows the same effect for ORR. I need to get my cursor back. Yeah. So just to raise this one so there's no confusion. It's nice to have all these tools in the presentation. Okay, ionic liquids. There has been some rumors that the ionic liquids have been observed. Nothing public, I think, but there's been an interest to study. And of course, we had to assume some relevant ionic liquids that could potentially have an effect on the fuel cell. So what you see here is we have two ionic liquids, both the same imidazole cation, but with a different anion. And as you can see, the anion looks very much like the end group of the PFSA membranes used today. So to me, it's assumed inert in the fuel cell environment. But we also used a slightly different anion, so we tested both of these. I think the first effort was to try to make a gas mixture, but the vapor pressure here is really low. So I think we made attempts to having gas mixtures for this purpose, but that did not succeed, because that would be the ideal testing, to actually have a gas to feed to a cell to test. And then Sintef tried some spray painting.
Okay, perfect.
Okay, so you can hear me now?
Yes.
Yeah, we have a bad connection to Norway, apparently.
No problem.
So where was I? Yes, so we tried the spray painting, but then we realized from spray painting that we would not be able to discern the effects of the actual just the solvent on the spraying on the MPL, in contrast to the concentration of the ionic liquid itself. So we sort of gave up on that strategy, but we did half cell experiments, and we wanted to see if we could see an effect of the ionic liquid on the electrode, and I think I have a slide later showing that that's not the case. And then we moved on to trying to do liquid injection at the anode for single cell tests. So yeah, so like I just said, not much effect on administering the ionic liquid onto a RD electrode. If we feed, so these results show that you have a single cell assembly, and you feed ionic liquid 4.2 milliliter per minute into the fuel loop. And clearly here we see, if you look at the chart, you see that the gray line with no contaminant. And then we have the first ionic liquid, and then we have the second bond, and clearly a much higher effect of the second bond. But there is some concern here about the integrity of the testing due to flooding. And also the problem with liquid injection is that it's sort of, it's hard to predict how it will distribute over the entire flow field of the active area on the anode. So I think we see an effect here, but this is work that needs to be reproduced in order to be able to conclude. Okay, so I think Sylvie, you can talk about the your stack testing.
Yes. Okay, thank you, Tor. So we also performed the stack testing as presented before with some toluene. That was decided for this work package on new or other impurities. So now you are used to this slide. We tested with the S2 stack in the hydrate conditions already presented before. And concerning the test program in this case, so in between the different reference tests, we did the different daily poisoning tests using 20 ppm of toluene. First, this concentration was selected with the consortium based on previous works. And then we tried to add some CO to this concentration of toluene. In the second series of experiment was with 0.5 ppm, and then we added 1 ppm and to see something, and then we compared with 1 ppm of CO only. So in this case, I am presenting first the results of reference test with, on the left, the performance losses under pure hydrogen. So during the different series of tests. So if you refer to the colors in blue, we have the tests before the poisoning steps, with including toluene. Yellow corresponds to the step after the contamination test with 20 ppm of toluene. Green is after contamination steps with 20 ppm of toluene and 0.5 ppm of CO, and red is at the end of test after contamination including 1 ppm of CO with or without toluene. So we can see that main losses occurred only after the final final contamination test with 1 ppm CO. Here we can have a combined effect with offload cycles, but it is there was still reversible losses observed after 8 series of contamination at the first part of the program. Concerning the tolerance to CO, we have CO tolerance which is not really affected before the test, again conducted with 1 ppm CO. In fact, if you could see, it's not very stable, but the experiments at the different moments, the blue, yellow and green are really similar, and the last case really shows an increased degradation under 5 ppm CO. So then let's see the degradation rates during the poisoning campaigns. So here, this is the assessment of performance losses. When the stack is operated and load the LCDRCs, like shown earlier today. So in this case, again, we assess the degradation rates for about 18 cycles. So here on the left, the small image is showing the degradation rates versus current density for different experiments. This is to show the kind of dispersion we observed. So orange data are with toluene and 1 ppm CO, and in red it's there are 2 experiments with CO only. So this is the examples for 1 ppm. On the right side, there are average degradation rates for the different cases. So with 20 ppm toluene again, 20 ppm and some CO, and then the mixtures with 1 ppm. So what we can see here is that we have always more or less performance losses at high current loads, like you have seen before. This is also the case when using only pure hydrogen. We have a clear negative impact, which is reached when increasing to 1 ppm CO, partially by comparing with 0.5 or 1. Same trends and same average values with or without toluene in this case. So what we can say from these results is that we have no visible impact possibly attributed to toluene 20 ppm, at least for this stack and these operating conditions. So for next steps, we could check if relevant the kind of results we could obtain in other conditions. And similar to the experiments previously shown today, what are the possible effects on the very long term? This was not assessed. So I let you continue for a small interpretation tour. Thank you.
Thank you, Sylvie. Yes, so we did some experiments looking at toluene with gas analysis in the recirculation loop, and what you see here is actually pretty clear that when administering 2.9 ppm toluene, what we see is an accumulation of the methyl cyclohexane. So we believe this probably the reason why the effect of toluene is low. But of course, would be nice to have and show here is the fuel cell test where we actually administer the cyclohexane directly to confirm this. But it looks like the toluene is decomposed, so this is probably a probable reason why we see a low. Okay, so sort of to try to sum up, as Christian showed, there were some limited information from the survey about the new impurities, but we had already quite a bit of input, so we could continue working on halogens, freon, ionic liquids. So that wasn't really a problem based on the data we had already from refueling stations. I think our current perception of halogens is that we think now the effect of the halogens are more adverse for the heavier ones. And to answer Martin Carré's question, yes, there has been found samples outside Europe with organobromide compounds in hydrogen fuel. Returning to freon, it's hard to conclude on our work because we have half cell experiments where we have no effect, and we see single cell testing where we see an effect. We're pretty clear since we did representative catalysts on the rotating disk that what we see is actual. Like I said, just showed the toluene. We believe that the effect is lower than what we would assume for aromatic due to decomposition. And for the ionic liquid testing, this had proved challenging because, firstly, we could not make a gas mixture with these ionic liquids. Spraying of NPL was not successful. Liquid injection is possible to do, but we need to sort of, I think we should do experiments with just feeding water as a blank to see possible interaction of liquid injection into the anode side. And on ionic liquid, I believe there is experiments that have shown a single cell effect, but we have not seen it on the half cell experiments done in this experiments in this project. Yes, and also most of these results should be reported. I don't think, and Jana, correct me if I'm wrong, that there is a deliverable addressing the new impurities. But regardless, we have pretty comprehensive work on the halogens, so we have a clear aim to disseminate this in a scientific article after the project. I think that was it. Questions?
Okay, so I think that Martin had 2 questions. So Martin, if you want, you can activate your camera and your microphone. So it is more interactive. Oh, I'm gonna give you the access. So Martin, to activate your camera and your microphone, you just have to click on the 2 icons that are red for now, but when you will click on it, it will turn green.
Well,
Well,
can you do it for her? Can you override, or is it?
yeah, the question is here. So, based on the results, do you think the limit value of 50 ppb can be increased for prions?
I don't think I have any or have enough evidence to change the current specification. My first concern would be that I still do not know if it's representative to report on a hydrochloric acid basis, meaning that you count the number of freons in the molecule. And I think we need more results. Another aspect is that we now see that the effect of bromine and iodine is stronger than that of chlorine. We need to consider that. And eventually, I think it has also to do with the probability of occurrence that we need to map that these iodine and bromine compounds will actually occur in the fuel. So several aspects, Martin, but I don't have it personally. Don't feel I have enough scientific evidence to change the current 50 ppb limit.
Hey, thank you very much for your answer. And this is the next question.
I think I already answered that one, but I have some evidence of not hydrogen bromide, but I have a brominated organic compound seen, but not iodine. I promise to show it to Martin next time we meet, but it's not public data, so I can't put it on the screen here.
Okay, so Martin is thanking you in the chat. So thank you very much for your presentation. So now I think that we're going to do a little break for the lunch. So I think that 1 hour break is right, Sylvie? Can you confirm it?
Yeah, sorry, I lost the microphone. Yes, this is 1 hour break in the agenda. Maybe again, if you can show the agenda of the afternoon to remind attendees, because I guess you don't have this in mind.
Okay, so I'm gonna let you the agenda.
Yeah, no, it's just well, this is the second slide. Yeah, this one.
Yes.
Well, so it is easy. We are starting with a session about sampling and hydrogen purity, and then we have the talk by Tomioka-san and the final discussions. But just to show to people that, well, it is about 2 hours and a half session starting at 1 o'clock Central European time.
Yes.
Okay.
Perfect.
Well, that's it.
So
well, thank you very much. And yeah, hear you later.
Yes. Have a good break. Goodbye.
Thanks.
See you. Are you here?
Yes, I am.
Okay, perfect.
Definitely.
Perfect. So I'm gonna put your presentation.
Okay. I guess I can just start. Yes. So also in this project, we have objective of mapping fuel quality dispensed in Europe. So this is the results of the sampling and analysis from refueling stations we have done. Yes, you remember the qualitizer we used extensively in Icora. It's what we call a parallel sampling approach, where we insert a T-piece between the vehicle. We have a T-piece in between the vehicle and the nozzle at the refueling station, and we bleed off with a high-pressure hose to 10-liter cylinder. The benefit here is that we don't need to override the operation of the refueling station, so we use a normal fueling protocol. But since Icora, we also had the another sampling strategy emerging, which is the HiSam. HiSam has a bit more flexibility when it comes to sampling, but it also has the capability of doing parallel sampling approach. So what we wanted to do in this project, we wanted to compare the two methodologies, basically side by side, when visiting refueling stations to collect samples with both strategies. So we had a sampling campaign in 2019, and this work is published in International Journal of Hydrogen Energy. So everything about this SC1 can be found there. In brief, we used the qualitizer. We collected samples from Norway, Sweden, and I was very tempted to say Denmark now, but that's Germany. We analyzed the samples with the project laboratories, ZPT, ZSU, and MPL. And since we used smart chemistry in the first, or in the Icora, we wanted to sort of compare with that by sending the samples for analysis there as well. Yes, so what we found in these samples was, like in Icora, what we generally observe is that the main challenges is water, nitrogen, oxygen. As you can see from the table here, the water is the main problem. For the first two samples with any content of water, we see ZPT reporting high levels, but the others elevated but not above threshold. Then we have a sample where NPL and ZSW report violating levels, and this one was not measured by ZPT. And then we had a sample where all three labs reported high values. And you can also see here that it's quite interesting that smart chemistry did only report water below detection, and with the exception of sample 6, where they had a value of 1.5, so systematically low. And it should be noted here that we use 10-liter cylinders, so the samples sent to smart chemistry were transferred from these cylinders to smaller vessels, typically between 0.5 liter and 2 liter. So it's possible that the sample transfer actually has an effect on the water estimate because of this. So if you look at, again, from the paper, so you can study, but this sort of shows the precision of the results between the labs. We see the violations, and we also see the spread between the labs, and we can see that smart chemistry here is low on all samples. For nitrogen, I think the accuracy is a bit better. at least the labs in some places are well aligned, even for elevated values observed. One exception here for smart chemistry is clearly an outlying value compared to the rest. Otherwise, fairly good correlation on nitrogen. So this is sort of summarizes what we found with both the mean value of all results. I guess my point here is that if the next to last column, we have the number of violations, and we see we have 4 individual violations for water, and we have 1 for sulfur. And if we on the last column say that okay, validation is only justified if 2 or more labs can document it, so then only 2 samples of water are out of spec. So that was sort of the finding in those results. So now switching to sample campaign 2, and I must say, due to the situation with COVID and travel, because this was SINTEF work, this was heavily delayed because of this, and eventually task overtaken by German partners because SINTEF could not travel. So we just received the analytical results and put them into a table. So there's still a bit of work on interpretation before we can conclude on everything, but that will come into a publication and the deliverable for work package 3. But what you can see here is that we, in this case, we have 5. So ZSW did the sampling here. They, I should say they, not we, visited 5 refilling stations, took 10 samples. They also mixed in some sampling for work package 4 into comparison. Thomas Bakai will talk about that later. But you see here that we used both sampling devices and also used different sample cylinder preparation strategies. So there's quite a bit of information or changes between sampling strategies here. So this is the first sampling campaign of the 2. So it's the second sampling campaign. And what we generally see is that there are no direct violations. We have methane in a sample, not a problem, it's just an observation. The tolerance is high. We have elevated helium in some samples, still not a problem. And interestingly, we see CO in, you can see here, I marked here. I should have said we found CO at 1 refueling station in both samples, but you see the labs here for both qualitizer and HiSAM are quite coherent with the resulting. The reporting is very good. I also put the water in bold because there is no violations, but if you look, it seems that in this series, ZPT and NPL are quite well aligned and ZSW a bit higher. So this is just an observation we see in this set. And also the nitrogen here is highlighted because in some of the samples here, ZSW and NPL are quite well aligned. And it's not consistent throughout the set, but it's just an observation. And also the helium, the elevated helium, we can also see is quite coherent between ZSW and NPL. So a set with There's no violations, and I mean the quantifiable impurities, oxygen, nitrogen, and water provide some information. And in this case, also we see that CO is present. And then we had a third sampling campaign, and this was done by ZPT. So 6 samples, 6 refueling stations were visited, 6 samples collected, but we also have 4 extra samples for backup that we can look into when we try to interpret. In this case, it was only HiSam sampling device, and I believe the sample, the cylinder preparation was also identical for all. Now, this slide is a bit more busy, and my first sentence there on only analyzed by ZSW so far is, I don't know why I didn't take that out, but my apologies. We have result from all labs there, obviously, so that's not. But what we see here, if you look, is that we have violation in water, we have violation in oxygen, and we have 1 violation in nitrogen. You see the nitrogen, to take that one first, is pretty, well, it's high, so the lab agree, but I guess the levels are quite different between NPL and ZPT. If you look at water, you see the problem here on the first samples is that ZPT reports these as normal, and you have 2 labs showing high values. On the second one, sorry, this one I'm showing here, sample 3, we have 2 labs in agreement and 1 in violation. So it's clearly a spread in the water assessment here. And there are clearly differences between the labs, so we need to go further into and see. But like I showed you in the first sampling campaign, also water was an issue. Oxygen, we see elevated levels close to tolerance, and even in one case we have a violation reported. For CO, there is 1 sample that's in violation. I should have marked the number from NPL should be marked with red as well, because that's also high. So the labs again with CO very consistent on the CO assessment. If you look at nitrogen here, I think the labs show better conformity on the results here than in the previous set. Some differences NPL here, but still a fairly good assessment. I've seen much higher differences before. Also on argon, quite good, consistent. Helium, ZPT not reporting the levels seen by the 2 other labs. That's an observation. And finally, we have by ZPT, we have 1 violation on halogens. I believe, and correct me if I'm wrong, Christian, that was trichloromethane that was found. And it's also reported on molecular concentration level and not multiplied by 3 chlorine. So this is a clear violation. So there is a lot of information here. We need to sort of, I think we just got all the results, put them together. We had some initial discussions, but clearly we need to revisit to look at this and try to analyze what could be the source of, especially water inconsistencies in these. Yeah, so I think to conclude, the project has collected the samples to reach its goal. We have published data from the first set. I think it makes sense to published the data from the second and third campaign as well into one publication. Like I said, the sampling campaign 2 shows very little impurity information, although there are, you can look at the laboratory performance by comparing measurable quantities. Sampling campaign sampling campaign 3 is a bit more challenging, and we need further investigation to sort of understand what's going on. And eventually, all the results there will be published in a deliverable, and also we make a publication on it. So I think that was it. I would expect some questions.
Yes. So there was questions in the chat, but Vladimir and Christian respond to it. But there's one more question from Vincent, which is this one.
Yeah, the root cause. So that's not an easy. Well, it's an easy question to ask, Vincent, but to answer is not so easy. For the water, clearly water is challenging to analyze. It's one of the more challenging analysis, although the labs used calibrated standards, etc., etc. It's seen that water becomes a problem. I believe also sampling strategy is sensitive to water. But I cannot answer. It's an observation in several sets that water becomes a problem. I don't have the answer. I see, Christian, you're volunteering because you put microphone and video on.
Yeah, just to support what you said, we just recently received all the results and put them together for this workshop. So we have to go to a deeper analysis on what has been measured, and we just had some first discrepancies in preparation of bottles and in purging at the station. But I think tomorrow we'll just put some words on this, but correct that we have to just go to deeper examinations later on to interpret those results.
Yes. I am not sure if we can answer that one better, Vincent. So maybe we should take another question.
Yes. Vincent said so there's no more questions for now in the chat. Vladimir is right, so maybe we should wait a little. Oh, it's a technical problem, so I will figure it out. So we can move to the next presentation.
So who could that be? Right. Okay. Also part of the, and this was actually planned in Hicora, but we never managed to convert and actually do measurements. But so I guess this was transferred to Hydrate, and the purpose was to do online assessment of hydrogen refueling station quality. And so our goal is that, like I said and showed you, we commonly see quantifiable amounts of nitrogen, oxygen, water, and sometimes CO2 in the fuel. So we sort of wanted to capture those, and we also wanted to have a method that could sort of have a wider scope and look for other impurities, assuming quantifiable concentrations. And we wanted to put this out for long-term monitoring. So our take on this was to use a gas chromatograph with a thermal conductivity detector for nitrogen, oxygen, and some of the inerts in CO2. And then use FTIR for the rest, not all, of course. H2S is difficult, but still has a pretty wide scope. The refueling station in Ulm, this was planned in Norway, but we had an accident a couple of years ago that prevented all experimental activity. We still only have 2 public stations open in Norway, I think. 3 if we count the one in Trondheim, that's semi-public. So experimental work in Norway was halted, but it turned out we could do this in Ulm. So a couple of weeks ago, we went down and installed our instrument. So in Ulm, there was already a bleed light from the station, and by installing this panel you show in the photo, you could reduce pressure, and through a 12 millimeter bleed line, we could provide hydrogen for our analytical instruments. So how did we do this? Well, we bought a fairly large suitcase where we fitted the FTIR and the GC. And of course, we had flow controllers for purging and devices, analog input output to control these flow controllers, power supply, etc. But the adaptation we had to make with respect to safety is that you see here that we have a hydrogen sensor, because this, if there is a hydrogen leak, we need to comply with regulations. So we have a sensor and we have a controller box that will, it has a set point about 10% of the LDL, so that's 4,000 ppm. So this will then, if there is an alarm, we will have a visual alarm, and it will cut off power to this system, and it will, we also have a solenoid valve that will cut off the hydrogen supply. You see the FTIR, we could not heat the cell. That's something we would do in the lab, of course, but we have a 10-meter cell, so we have pretty good scope analytically. So far we haven't much data yet. Been some challenges. We actually found out we needed a lot of purging to get the line to get the water level and CO2 level down, so we can actually start to monitor. So what you see here in this 3D plot is basically you see some water here, and this is the CO2 signal. And if you take this into 2 dimensions here with an offset in the ordinate axis, you can see that there is quite a bit of variation in the CO2 level over time. So that's what we're currently observing. So if you see here, you see the CO2 again, but this also shows the water. And the reason for the negative is, of course, that for FTIR, absorbance is relative to your background. So when you pull a background, you have a certain water content in that, and with a negative signal means that we actually have lower water content now than we had in the background. So that's why we get these. So, but CO2 is increasing, and what we're a bit puzzled about is that you see it appears to be CO2 fluctuations. These levels are low, so there's no concern that this is absorbance. We still need to do some translate this into concentrations, but this is very low concentrations, but we still see fluctuations over time. We would like to understand what this is. Looking at the GC, the top chart here shows you the integrated area of the peak, and well, it's a measurable signal. And at the bottom we have tried to integrate. It's still a bit crude because we need to set a decent baseline for the integration and conversion. But basically we're looking at around 10 ppm levels of nitrogen. And we get a bit more time data here. We'll probably improve this. But you clearly see how the instrument responds when we switch from hydrogen to helium on the purge side. It actually goes to 0. So yeah. So that was sort of what we have done so far. It's a bit sad that we had to do this in the last month of the project, but luckily there's possibility that we can possibly continue some of this monitoring in Metro High-B, since we now have it established. And I think also important here when you do this is to actually take actual samples to see if the samples collected at the nozzle are coherent with what we see when we monitor the quality online. Okay, I think that was it. Questions?
So there was questions in the chat, but Christian and Vladimir answered to it.
I think that's not a question for me. I think that hydrogen producer supplier should answer that one.
Okay, so
I think it's important here then to sort of what we have looked at several times is to look at the impurity level at the nozzle and at the production, if let's say at the inlet of the refilling station, if the water level is the same there as it is at the nozzle, because it's not necessarily the fact that the production is high on water in hydrogen, but it could be the refilling station. And this is very often the case for nitrogen, because nitrogen doesn't come from production, it comes from the refilling station itself.
thank you for your answer. Someone is typing, so I don't know, maybe there's another question coming.
If I may, about the question of the reaching 0.5 ppm. I mean, as you may have noticed, there is some already discrepancy on the water measurement. So an additional challenge, if they think about reducing the spec to 0.5 ppm, will be the ability to monitor it, either online or either by measurement. I think it's something that could be challenging if we want to implement it tomorrow.
So there is one more question.
Yes, I think we have looked several times for this, the apparent ratio of nitrogen, oxygen. Sometimes you can use argon as well to look for air leak, but I don't think in any of these sets we have said an indication of air leak into the sampling. It's very obvious if it's there, and we always look for this. So.
Okay, so thank you for your answers. I think that we're going to do the next presentation. Thomas, I think it's yours.
Yes.
I'm gonna put your presentation. This one.
Yes, exactly.
Perfect.
So just to change a bit. So I'm Thomas Bakker, and I will present on behalf of NPL, ZBT, and ZSW, and especially around the three laboratories, and trying to bring a bit of information around the comparison of the different laboratories. First of all, I just would like to remind a bit about the situation when we started the project in 2017. So at this point in time, in Europe, there was a really limited offer of analytical laboratory that were able to do the measurement of hydrogen fuel quality, and a lot of samples were sent to the US for analysis. As you see, since then, there was a lot of increase in terms of the number of refueling stations, and it was critical that Europe develop a kind of capability, especially if you imagine sending a lot of samples to the US for analysis. And that's why within the project, our objective was to set 3 independent laboratories and to try to get a kind of a reliable network in Europe. The 3 laboratories or institutes are ZSW in Ulm in Germany, ZBT in Duisburg in Germany, and NPL in Teddington in the UK. I will present where we are now because I think there was a lot of progress in the last 3 years. But here you can see for ZSW that they have all the capability to perform measurement according to ISO 14687. What you will notice is the type of instrumentation they are using is a mix between gas chromatography and OFCEAS. And you will see that they are able to report their calibration range, LOD and LOQ, that are in coherence with the ISO and the EN requirement. And they have sampling capability through the ISAM, and they are able to operate the qualitizer too. When we look at ZBT, another lab, you will notice that they are using different type of instrument. Again, a lot of gas chromatography, but a different detector, PED, and significantly higher IMR-MS and EI-MS. So here we will see a different type of instrument, but again, their limit of quantification are definitely coherent with the ISO standard. In terms of sampling, they will use a ISAM, and they require roughly 300 liters to perform the analysis. So again, another type of lab, another kind of setup, but they have the capability to. Finally, here we will see NPL. So here we are using a mix of gas chromatography and SIFT-MS for most of our measurement, and we are able to do sampling too using the qualitizer. So that means that we have 3 labs, different type of instrumentation, but they are all capable of doing sampling and analysis according to ISO 14687. But now that we have labs, and I would say that in 2021 there is more than 3 labs in Europe that are capable. Does it mean that all our results are equivalent? And probably that's echo one of the questions from the previous talk from Vincent. Here I took an example from a previous project, ICOR, in 2017, where Smart Chemistry and NPL were analyzing the exact same samples. And what you can see here is that, I just need my cursor. Yes, here you will see that we have some differences in some of the measurement, especially in this case. You will see differences on oxygen, some differences in nitrogen, water, and in one case it was on non-methane hydrocarbon, especially on methane. These 2 laboratories at this time, and I think Smart Chemistry was one of the reference in the US, and NPL was performing a lot of measurement in Europe. Question at the end is like, how can we trust laboratory result, especially because you will not appoint 2 or 3 laboratories to do one measurement? And I think one of the answer is actually that the laboratories are demonstrating their capability and their comparability through intercomparison. And probably that's something that we have done through the whole project of Hydrate. And here is a bit of a illustration of how we have progressed over the timeline of the project. So in 2017, we start to use some reference material, so which are synthetic hydrogen mixture with a non-amount of chemicals inside. And that's really useful because that will allow laboratories to progress internally. Then we decide to compare the different partner using the sample of the sampling campaign 1, and we compare with smart chemistry. That was the first, I would say, internal inter-comparison, just to start to realize how we benchmark. After this, in 2019, we decided to join an inter-laboratory comparison. So it was Metro IV1, where we actually benchmark ourselves against 10 other labs worldwide. And then we went for an even more complicated exercise because we decided to perform a sampling and analysis inter-comparison. So meaning that the 3 different labs were initially going to sample and analyze the sample that they have taken, just to simulate what would happen if you ask a laboratory to perform a measurement for a customer or for any project. So you see that it was kind of increasing in terms of complexity. And I think this last exercise is probably one of the most interesting and most complex realization we have done. If I go a bit into detail about what has been done, so within the project, we have developed some reference material. So here you see like a kind of composition for inert gas. And what is really useful is when you start doing this analysis, when you work with a reference material, you can do as many measurements as you want in your lab, see how your different systems are performing. And this is kind of an example here. You see one lab that was performing some measurements using multiple detectors just to see how they benchmark. This is quite useful, and it's a good learning curve to develop and validate internally a method. There is a bit of a limitation to this approach because currently it is not possible to find all the compound in ISO 14687 in reference material. And that's why we decide to do some inter-comparison using the sample that we have taken in sampling campaign 1, expecting that they will probably present a bit more, they will represent a bit better what will happen in reality. And at the same time, they may contain some of the reactive compounds that were not available in the reference material. So this is the same graphic that has been presented by Tor. Here you can see that on nitrogen and water, there was a little bit of disagreement. But it's really important when you're for an analytical laboratory to look at this. If you look at the water amount fractions, you will see that some labs, so the orange, blue, and yellow here, are reporting, I would say, in a similar order of magnitude. There is discrepancy that will need to be, I would say, refined. But what is interesting is the result in gray from smart chemistry are really different. And at this point, it's really important for the labs to actually look into how they are doing their measurement to probably realize that there is a need for corrective action plan. I suspect at this point, smart chemistry looked into their gas calibrant because it could be a problem why they are always reporting below limit of detection, why it was actually probably not below limit of detections. Again, for nitrogen, we see that there was some observation, but on overall, there was a good agreement on most compounds. So what is important is here, through this exercise, I mean, the lab were able to identify some discrepancy and actually make some corrective action plans. For formic acid, it was NPL that was having an issue, and we just realized that we had an interference and we had to change on our methods the way we were getting our result, because we could have potentially an interference with ethanol and methanol that could have created a fake positive on formic acid. So here I will not really discuss the result. I would just see that if there is a disagreement, it's really important for a lab, because it's how we will improve and get more reliable. All of this result has been published as Tor highlighted. Then we did an interlaboratory comparison So it was part of Metro IV1 program. So it was on hydrogen sulfide, carbon monoxide, water, and nitrogen. The laboratory on hydrogen were actually performing quite good. Okay, in most cases, if you're interested, probably some of the hydrate lab may disclose their actual reference number because everything has been provided anonymous. But I would say that we have done a pretty good job to be in between the green line in most cases. But probably moving to the most interesting activity that we have done is the sampling and analysis intercomparison. So here we have performed a study comparing or performing dual sampling using the ISAM and the qualitizer. And actually, the qualitizer was the sample for NPL and the ISAM was a sample for ZSW and ZBT, representing what would happen in a real scenario. And we have done this on several refueling stations, so that gives us like a kind of we reached a statistical number to have a look at differences. Here is a kind of a snapshot on the result. So you will see here the result of ZBT using the ISAM and their own cylinders that they will use for this, prepared the way they normally do it. ZSW will provide result on ISAM on their cylinder 2, and NPL on the qualitizer using their cylinders. What we observe is there is a fairly good agreement at the end when we look at the result, especially when we look at CO, formic acid, ammonia, sulfur, halogenated CO2, methane, or argon. Once we were able to see something. So especially these samples probably is one of the most interesting because we have a really good agreement on argon. We notice some discrepancy on nitrogen. CO, we have again a really good agreement. Then, some questions were raised around, again, probably the same compound that we had before around nitrogen, oxygen, and water. As I mentioned, there is a bit of discrepancy here on the nitrogen measurement. Slight discrepancy here on the oxygen too. Here again, I think it's really important exercise for laboratories because it's probably the only way for us to understand if we have a bias against other methodology or other labs. And if I want to kind of highlight it, I will move here. Here we were actually, the three labs were measuring the same samples. So ZBT, ZSW, and NPL measure the same sample that has been taken by the qualitizer. And then we measure the same samples that has been taken by the ISAM. Again, CO, we are perfectly aligned. Argon, we are perfectly aligned. Again, helium is fairly good. When we look at nitrogen, we will see that ZSW and NPL agree a bit better when they are measuring the same cylinder. So again, that will be really useful to get another level of understanding and probably to kind of realize, okay, we may have a little problem on this compound. The other labs are actually slightly higher or slightly lower. We'll see that the water is aligning again a bit better when we are looking at the same cylinder. When we actually looked at the systematic comparison between the qualitizer and the ISAM, and because we have repeated this exercise, we realize that we are probably able to identify some small differences. So that's something that we are currently looking into it, but we have noticed potentially a small difference between the sampling with the ISAM and the qualitizer, which is, I would say, some people will consider it negligible. We are probably talking about roughly 1 or 2 ppm of nitrogen and slight differences if you look at oxygen, that slightly look higher. So again, this is quite important because it's something that will be extremely difficult to identify if we are not performing this type of comparison. And it will impact actually all the results that we are providing to the industry. So just to conclude, now we have 3 independent laboratories that are capable of ISO 14687. You probably realize that there was a lot of progressions over the 3 years, and it was probably thanks to a lot of benchmarking exercise that we have progressed so much. We have compared with the US laboratories reference, and I think we kind of demonstrate that in Europe there is really reliable analytical laboratories, and we have benchmark in this international comparison where we have performed fairly well. This sampling and analysis intercomparison, and I think we are just at the beginning because, as we explained earlier, we just get or gather all the results on it recently. I think it will be quite important in understanding discrepancy between sampling system, and probably to start and help on how to standardize or improve it. If you look into this, we have compared 2 sampling systems, 3 laboratories, and if I consider more than 20 different analytical methods, so there is a lot of variation possible here. What we realize at the same time is that there is still a lot of challenges. So water is still complicated to measure. You have noticed that there is a lot of discrepancy still between the labs. That's something that we will need to improve, or to understand how we can improve it. Reactive compounds, you notice that the laboratory agree, but at the same time we are not able to measure anything. So it's probably it will probably be required to do a similar exercise when there is actually some reactive compounds to measure. And this is a limitation of doing intercomparison with real samples, is that currently they are too clean to offer this this level of contaminant. So that's why, I mean, once reference material will be available for reactive compound, I think it's something that will need to happen. That link to the next part is reference material has been a bit lagging behind, so we probably were too fast. But I think it's something that Metro IV2 project will try to tackle. Representativity of sampling, it's something that we just started to touch upon. I mean, with the comparison of the HISAM and the qualitizer, and I think there is still a lot of data around it. Sampling conditioning, it's something that we start to compare with sampling campaign 2 and 3, how the sampling conditioning may have affected some of our results, especially for oxygen, nitrogen, and water, which are the ones that can be the most influenced by the conditions. Just to summarize, now we have 3 laboratories that are available in Europe, and that's quite important because now we are hoping to continue after this project to support the hydrogen economy, and all the analytical laboratories that will enter or join this activity. As something probably to take upon or to think about, I think there is a lot of things that we discuss that would probably be needed after this project. I mean, the laboratory will not disappear. I mean, it's something that will stop. And I think it will be quite important to continue to benchmark between laboratories. And one important thing is how or within which framework we can continue to do these discussions and comparison. What has been highlighted too by our work is that water analysis and reactive compound are definitely something that will need to be improved, because we still see a lot of discrepancy, not only between the 3 European laboratories, but you have seen that smart chemistry was outstanding too. Sampling intercomparison, I mean, as mentioned, we start to touch upon it. We will have a lot of work in Metro IV2, but it's probably something that will require, after the intercomparison, maybe some refining or standardizations. Most of our work will be shared with ISO 19800-9, which is looking at the sampling standardizations. And probably there is more into standardization that will be needed. Finally, I think what is quite important and probably one of the main outcome from our group is I think the 3 labs will be happy to continue to apply their sampling and analysis capability in Europe. And that will be really important to understand better the hydrogen quality in Europe from the refueling stations, and probably be useful to be or to support all the uptake of hydrogen outside of transport, where they may have similar problem around hydrogen quality. And with this, I will finish my presentation. So if you have any questions, just feel free to ask.
Okay, so thank you very much. I think that there's no questions for you in the chat. Your presentation was quite understanding.
Okay.
So thank you very much.
Thanks.
So the next speaker is Hidenori Tomioka. I'm gonna put your presentation.
Okay, great. Now, at first, thank you very much for just inviting me to just telling about the situation in ISO. And it is kind of that still old story, and also that it's still going on. So then I'm just covering that kind of the historical thing. So I'm sorry, how to point. Which one? Oh, no, here.
So you have a little pointer.
Point, yes. Okay.
Oh, perfect.
Can you
Yes,
see?
You can see it.
Okay, great. So then the first. Oh, that one. Let me. So this is the always I show that while that ISO meeting. So then this is that schedule chart, and then I think it's going to be the final chance to show you that this kind of stuff. So then historically we have that older version of the part 2 of work ISO 1478, and then we had that 3 grades here, and then it's already published in 2019. So it just gathering that originally it had the 3 parts, and then we gathered that 3 documents to 1 document, and then that document was published in 2019. And also at the same time, we have that the problem of that need to have that quality control method as a ISO standard. So then we also started at the same time, and also it finished in that at the same time of the 14687. So, and just add up for that quality control standard. So then we need to change from that the original document is aiming to that part 2 of original 14687, which is for the hydrogen fuel for fuel cell vehicles. So then it just needs to change that to align with that new grade D 14687 document. So then just we use an amendment system, and then it's just published last month. So then we just going to start that new revision for this document. So then I'm just telling a little bit more detail for that. PUD. And so this is that story for that working 27, which is for ISO 14687. And then and this is that new project, which is revising the 14687, which is published in last 2019. And they had just started, and it's a new project registered. And so then we haven't had that submit the working draft net, but still that we're working on that. So just we're preparing that, not reached here, but the working draft here, and also just aiming to publish this document 2024 February here. So then we have just one virtual meeting, and I haven't I missed to write them here, but we are going to have a meeting next month, so October 11th and 12th. So then I'm very sorry here because that the meeting time in Europe is quite late, and so then I apologize for the part. But anyway, the time of the meeting it's just rotating. So then next chance maybe it might be better, but still that next after next also you have that quite early morning session. So then anyway, just it's just happened this time. And so this is the whole system of the 14687. So we have 3 tasks. One is for the grade D, which is for the PEM fuel cell vehicle, and it's grade D. And task 2 is grade E. It is for the PEM specialist. So mainly for that kind of the station application of that, mainly used for that power generation of the heat appliances. And task 3, it is for grade A, and also it's going to cover in grade B. And it is telling here is the combustion and boiler and the heat appliances. And originally, still that it's written that task 3, so grade A is for that. The first thing for the application of this grade is internal combustion engine for transportation. So then it means that if you provide the hydrogen to that engine, hydrogen engine vehicle, so then you need to use that grade A. But it just kind of we need to avoid this kind of misunderstanding here. So then we are going to remove that internal combustion engine application from grade A, and we do not put directly into the grade E. So then in a grade D, the footnote of this application, it just saying that this grade A may be used in the application for that internal combustion engine. So then for that purpose, it's a kind of a little bit, we have that little bit flexibility for the PUD. So the bigger thing for us to avoid is that now at this time we have that, if we have that 2 category of hydrogen fuel dispensing at the same market. So one is for the hydrogen fuel for fuel cell vehicle, and one is the internal combustion engine. So then the big difference between those categories, and we need to avoid the cross-contamination of these gases. So then, especially for the fuel cell vehicle, it's going to be the big problem for that. But so, and also the number of the cars in market, vehicles in market. So we do not have to care for each by each. So then, so we not still need to see that those applications going to be spreading out in the market or not. But at this time, we just only set up for the fuel for the hydrogen vehicle on only grade D here. So then we're going to change that system like that. And so then this figure is just originally prepared by Martin. So then it is very good described that the hydrogen quality standard system. So then we have that ISO 14667, so it is a quality hydrogen quality specification, and then we have that 21087. It is for the hydrogen analysis for the fuel cell vehicle, and also that 9880-8. It is for the quality control. So then this basically these three standards for the keeping the quality of that hydrogen fuel. And then also we have that here the -1 of 1980. So it is that telling now in the sampling and also the filter. So filter is for that just specify the kind of the mesh of the filter, and it is for the covering that particulate specification in this standard. So then also the sampling is also included in this station document. But now that we're preparing that, so Tosan is the combine of that working group 33. It's covering that sampling of the fuel hydrogen. So then hydrogen quality analysis, and it just started. So maybe we had this meeting Tuesday. Maybe Tuesday or Monday in Europe, and so just a second meeting what held, and then we just started how to make up that sampling method, and also that for how to clarify those systems, and then we are trying to make it a little bit more simpler way to covering those quality hydrogen quality standard. And so then just needs clarifying that and how it specified. So the working 27 is the threshold specification. So it's in the grade D. So it is a quality for the fuel cell vehicles, and so, and then it is a grade D of this document. And the working 28 is covering that hydrogen quality control, and then. I'm just a little bit more detailed later. So, but we have just finished that amendment of this document, and also it's finished to 2019. That it's a collaborative work with the TC 158, and Joint Working Group 7 is just covering that analysis method for fuel cell vehicle. So those three standards are just keeping that quality of the hydrogen, as I mentioned. And as you see many times that this is a grade D of TC-7, and it originally was 14687-2. It was published in 2012. So not big difference between that, but maybe that nitrogen and argon is just changed from the 100 to 300. Also that the group of the carbon monoxide and the formaldehyde and formic acid, which is from that these numbers to that, so formaldehyde the 0.21 to 0.2 ppm, but also that the sum up of the three these species is also 0.2 ppm. So then added that a kind of a change from that the 2012 version. So then now we have started that new revision for that how which is going to be, but still that we seeing that a project in Europe here. So then we are going to have a kind of the data based change, and so then we are going to start the discussion for that each constituent listed here. And then the stories here is just coming from that to seeing that big wider this market volume for the fuel cell vehicle. So then we need to take care that production and quality cost, and so then quality control cost, and so then so the basic movement for this revision is going to the direction in the relaxation of the specification number, but still that discussing the kind of that sulfur compounds and also that halogenated compound. So then it's coming up more data, and so then also we need to discuss. And this is the kind of the comparison between that how to protect the SCV and also that market issue for the hydrogen. So then still we need to effort to decrease that cost of the fuel for fuel cell vehicle. So then we need to take care from both sides. And also, if that the market going to be, so then everyone can try to dive into this the market. So then we need to take care for that. I just tell the bad guy, and so then provide the cheap and poor quality hydrogen. So maybe that the particular standard here is still the many holes to pick up something bad. So then maybe one big topic is how to determine the purity of the hydrogen. So then we have that using the hydrogen quality index for the hydrogen purity. So then there's a long story for that, the terminology for that part, but still we need to take care of the quality, purity as a quality. So then we need to discuss how to manage that part. So then there are some topics to devise them. So then we just started. So then we need to prepare this new specification in 2 or 3 years time frame. So then we need to have the big collaboration among the European and also that United States or North American countries and research works. And this is that another one. So the working 28, which is covering the quality control. The name of the document is 1988-8. And just as I mentioned, so then I just published the amendment of that original document last month. So then the title of this document is telling that the hydrogen quality control and amendment 1 alignment with the grade D of ISO 4687. So then that just the structure is like this. Let me show that the figure just showed previously. So then originally then it had that ISO 4787-2, which is published in 2012. And this document, Quality Control, the 1988-8, 2019 version, the first edition, is just aiming that the standard or specification listed in this document. But as you see that soon after that, so that new ISO 4687 grade D was published, and at the same time when it published, the older version was cancelled. So it meant that the document which looking at was disappear here. So then we need to cover that gap as soon as possible. So that was the situation when we started this amendment work. So then, as I mentioned, so then this amendment document was published yesterday. So then properly just aiming that specification which is listed in the new document. So then we are safe now. So then we just started, or we just starting that new division. So then it was a discussion in, it was still before the COVID-19, but just we had the in-person meeting in Grenoble, which is held in 2019 December. So then at that time, so we have the discussion that how to cover that gap. So then, if we try to divide the full version of the document, so then it would take a very long time to take care. So then we have decided that just we change that document from the older version of for the -2 document to the newer ISO 14678 document. So then just we had started that time, and then just 1 year and a half time frame, we just covered that change. And then as you see, that amendment was published last month. So then I'm a little bit relieved. But then after that, so we just start discussion of that new division, just along with that division of the 4687, the quality specification document. That is the story for that to document for the fuel quality and quality analysis method document is still in that sense. So then just I'm wondering if any chance to revise this document. But anyway, so it's a kind of the fun right now. Oops. Then. And just I'm trying to cover the other document which is handled by TC197, and just it is kind of the reference for you to just information for you to check what kind of standard is just working with and TC197, and maybe that now working 5 is in the connector and it's the new version published, but also they are going to divide that document for covering that heavy duty or high flow nozzle and receptacle, and also that we are having that working 15 for that cylinder for the tube on stationary storage. And other thing is for maybe that kind of the interesting thing happened. So then just working, this is working group 24. And it originally just developed that station document, so 9080-1. It is for that fuel station and general requirement. It's published about 2 years ago. And then we are just creating that fueling protocol. And then we just need to cover the same number working group. So because that stakeholders of this technology is just the same as that original station standard. So then after that, so then working 24 is covering that. And they had the 3 parts. And the first one is that a kind of a general requirement, so the design and development process for that fueling protocol. So which is covered that a kind of the Bible of the fueling protocol development. So then you can create any kind of protocol which is suitable for that one particular occasion or other situation. And the second one in the -2 document is for that definition of the communication between the vehicle and the station. So then still that we need to discuss how that communication should be. So then we have that determined that IRD communication this time. So but still that we are discussing other new method or of that communication. So. Yeah, and third one, it might be the kind of the big interest here, but part 3 is covering that heavy duty vehicle. So then the high flow or some other flow model is going to be take care. But still that made a kind of a new working group. So covering, so just has started. So then for the part one document, we have that a couple, two virtual meeting were held, but still that in part two also started, and part three we haven't had meeting yet. So then just they're preparing that and how to manage that thing. But still that we have that need to take care of the technology itself. So then anyway, just as I mentioned, it just started. So please look at the progress of those in a couple of years. So then the 27, 28 for the fuel quality. And just I missed that joint working 7 for the analysis method. So because it just disbanded and after that. And so then still that we do not have any particular plant device. So then but still it's okay. And also that the working group 33 is part 9 of 9880 document. And so then it is sampling for the fuel quality. And then TO has just handling that. Maybe we have the 2 meetings, and then we are starting how to manage that sampling method. There's some anyway discussing that the last session. So then it was still that we need to take care and also handle that how that the standard should be. And then that is that ISO matter. And then just after that, I'm just introducing that how that things happen in Japan, that the heavy-duty vehicle fueling. So then, and so as you see that we have that so-called needle. So it is a new energy development organization that stands for that naming. So needle, and this covering that kind of the national project. And then one of that now we have that to build up that research center for the hydrogen advanced technology, which is for that fueling for that heavy duty vehicles. So then a testing station is going to be built under the national project now. So then what we need to do is just we need to build that testing station in a quite short time frame. So so we need to build up maybe a year time frame. So then looking at that technology for the heavy duty vehicle, so then or high flow nozzle or receptacle, so that or high flow fueling or dispensing system, we do not have a good technology now, so not established one. So then we just trying to make up something make it the more realistic way to build them. So then we have chosen that method. So we call it medium flow. So then maybe 1.5 higher flow rate device can be developed in maybe that easier way. And then if we put twin nozzles here, so then the number of the maximum flow rate is this kind of stuff. And then anyway, 3 times higher than the original light duty vehicle flow. So then device. So then maybe this is one of the realistic solution to build that heavy duty station in a very short time frame. So then just we chose that this mechanism, and also that we are still seeing that high flow nozzle. just we seeing that now 5 times higher than that normal light duty vehicle system. So then it is that. So maybe just I do not tell the detail here, but just now we are seeing that 87.5 megapascal for the operation pressure, and the fueling capacity is like 80 kilograms. And maybe you're just looking for at the 100 kilograms per car, but still that just fueling amount, then it might be enough, which had that 80 kilograms here. And then the basic structure of that site, and so then it is that concept diagram, the research center, so that it means that heavy duty testing station. So then we have the hydrogen supply, and also that we can get the renewable hydrogen from the renewable energy, and then we have that the supply hydrogen supply unit, which have that the compressor and also the tanks for that the unit, and then the main stream is for that this medium flow, the double outlet here, and then dispenser had the 2 hose and nozzles here, and then the heavy duty car can get that the double nozzles fueling here, and also that for the purpose we have that also light duty vehicle outlet, but still that it's also the double nozzle. So then in a situation in Japan, we still that seeing that the capability to have that normal two nozzles fueling using normal flow, then maybe it can cover that and not giant vehicle, but the smaller heavy duty vehicle in Japan. So maybe that it is also the solution for that part, but still that we have that aiming that final the target, which is for that high flow. So then I'm not quite sure if that technologically issue there, but still that we are waiting for that the new technology of the high flow nozzle and receptacle, and also that other devices like piping, also that hoses. So then we need to take care of those, or the whole package of that station or dispensing system for the high flow fueling. So then we just also trying to get those kind of information, and also if we can get those kind of the technology, so then this particular site has that also the capability to fuel, supply that fuel for that high flow outlet. So then still we that the project itself is going to finish in next year, fiscal year, but still we expect that using this facility to discuss or to perform a project of the development for that heavy duty vehicles. So maybe this is the last slide for me. So then thank you very much for your attention. So then, so if you have any question.
Yes, I think that there's no question for now in the chat.
Okay.
Maybe they will come.
Okay, thank you very much for your
you.
attention.
So maybe now, Alexander, you want to talk? You can activate your camera and your microphone.
Okay, Herman, thank you for this very interesting presentations. it's now my role to give a final maybe wrap up for this entire day. And I would like to invite all the hydrate partners maybe also to open their microphone and camera, so that we can actually see everybody who was involved in this hydrate project. And I would like to open that last session here and enable everybody to ask further questions regarding the presentations during the day. Any comments, any feedback from the audience? Highly welcome. Before someone starts to ask, I would also thank you all from the partners here for having that interesting presentations. We were also involved in all that activities from ZSW side, but we are no work package leader, therefore we had no direct presentation today. Thanks for that good work here. I think we had quite interesting results. Also some interesting questions from the audience, and again the invitation to have an open discussion and good wrap up for this workshop here. Who wants to start? Does everybody has the chance to open its microphone to ask a question? That's a more technical question from my side. Or how can we involve all the participants here?
The participants can only put messages on the chat. So there was a comment from Vincent. I'm going to show you here.
Is it technically possible to give everybody the chance to open his microphone and ask questions?
Not everybody, sorry.
Not everybody? Okay.
Yes, it is. because you didn't, you still, we are less than 25 in the room, so everyone can have access.
Okay, but so the only chance for the participants is to write questions. Did I get that correct?
I actually modified the interface, so now it's in meeting mode and everyone can activate camera, microphone.
Okay, perfect. Yeah, thank you. So I saw your question, Vincent. Do you want to directly talk in the microphone? Or should I just read your question? He wrote very interesting presentations. And will the presentations be available? I think yes, correct?
Yes, they will be.
Yes.
Okay, so the presentations
they will be on the website.
Will be available on the website. So that's the answer to your first question, Vincent. Thank you for that. Any more questions from the audience? Please open your microphone or write your questions. Okay, that's one question here. From Japan, do you want to?
Oh, yes. So
yeah.
Then just as a as a comment or a question from the ISO side. So then I'm just impressed to hear or see here that the very deep the research work in deep manner, and then especially for the carbon monoxide and also sulfur or some other species, and then also that you were trying to get the data from the stacks. So then I asked or just mentioned the morning session, but we also always had a question that if there any big difference between the stack data and the single cell data. So then I'm really interested in the data itself. And also, and my question is that is there any kind of that proposal for that change that specification itself. So then we are going to have changed this, or might have changed the specification, but we need to take care in 2-year time frame for this revision. So then if there's any the kind of particular the proposal for that the revise of the specification, then and I don't see, I don't have to see now here, but is there any chance to the proposal here or not?
Okay. I have no clear answer, but I think it's a very interesting topic. So yeah, in the past, most of these measurements were done on single cell level and small scale active area. I think it's important to also perform those measurements on a at least larger active area, more in the range where we actually would like to see the stacks later on the application, not only in the laboratory. That's what we try to do here. And yeah, also having more cells in a stack gives a little more information than just a single cell. I think it's quite challenging to give a recommendation about having a standard stack, because the impact of the flow field geometry and the active area itself and so on and so forth has a maybe huge impact on the results. But from maybe a small comment from our side here from ZSW, we are currently working on a more generic stack design, which will become available within half a year. And this is an open source stack hardware that becomes available for the public. And maybe these could be an approach of having stack hardware available for these kind of more realistic, let's say, full-size scale testing.
Okay,
that's a quick and dirty answer from my side. Any further comment from the colleagues?
From my side, as I tried to answer before, I fully agree that we should be able to link all these results we already have on single cells to the results we could get on stacks. However, the problem is that there are many reasons, but so many reasons also done with older components. So it is also a question of being always state of the art, and this has an impact for sure. We could see today two stacks, probably different components and different reasons. Yeah.
Maybe we have that the specification now is that there are kind of hold a weak point there. So then maybe the main topic needs to be covered, the total something. So then total hydrogenated compound, total sulfur compound. So those stuff, it's quite a something there. So for that analytical part, everyone argue me to just and so the rich species needs to be covered. So then for that, seeing that hydrogenated compounds, so then Tor has that mentioned that there are data is piling up like that. So then we are just trying to cover that chlorine compounds, but still that there are we need to take care of other things. So then I said that we need to prepare the 2-year or 3-year time frame, but still that we have the time. So then if we have, or you can check or have that kind of data in still that the going on and that result for that next future. So then it's going to be cover also that new revision. So then I'm really expecting that this. So this particular project going to be finished soon, but still that maybe you have that next stage of this project. Then we are anyway going to expect that kind of the new data, and also that so any division needs to be based on that technical data. So then it is obvious. So then this continuous activity is a great help for us, so that standard development side. So then, anyway, just I always appreciate that activity here.
It's an interesting topic. Thank you for this comment. I think also one of the very first questions from Garo Todd within the chat here goes in the same direction regarding the MEA description. So I think it's very important to open all the information that we need to get a final assessment of the measurements that we actually performed within different projects. And from my personal point of view, I think open source or opening all the information as good as possible would be very helpful for the entire community. Any further comment in that direction here, or some other issues to the colleagues which gave presentations?
Hello, can you hear me? Ask a question?
Yes, of course, go ahead.
So I was wondering regarding the presentation with the hydrogen sulfide in combination with CO. I was wondering if, since it was mentioned that you were able to identify better basically the mechanism, the degradation mechanism, even though the hydrogen soak and did not actually was beneficial for the recovery step, if you have thought of an alternative mitigation strategy or recovery step that could be used for automotive applications in this project.
I think that question goes in the direction of ZBT colleagues, maybe.
Yeah, I think Ulimi, as he's not here available anymore, so I think. But what we did there is just, I think Yari, you just can also put some words on this. But we just tried to figure out different recovery strategies, and we have seen that just only leaving this stack for this pause and leave it cooled down took some effects on recovery due to hydrogen sulfide. But Yari, maybe you can elaborate on this a little bit more.
Yes. Sorry, I'm not sure if you can hear me.
Yes, we can hear you.
Graham, we can hear you. Yes.
Oh, perfect. Sorry, so we did have some further experiments where we were trying to recover stacks in a more aggressive way from sulfur contamination, and the results weren't really ready to be shown today. Broadly speaking, we tried two methods. One with some ozone, which would obviously be a kind of offline attempt to recover from severe poisoning. Because there was some previous single cell results that showed that might be successful. Unfortunately, that obviously just caused a large amount of carbon corrosion. One which looked a little bit more promising, but we're still, trying to correlate the data on, is to starve the anode of the stack for a very, very short period of time, raising the potential and oxidizing off for absorbed sulfur. And the first results for that look quite promising. So hopefully that's something that will be an output from this project, but not for another few weeks or so. I'm happy to follow up on that offline also, if it's of interest.
Well, thank you very much.
Yari, do you want to also comment that?
Yeah, just briefly that the hydrogen soak experiments, they were trying to represent the short-term shutdowns of the real systems, like in automotive systems. And ZBT did also the longer shutdowns where we allow oxygen to diffuse on the cathode. And then there was some recovery. But of course, the amount of shutdowns was quite low, but there was an effect as far as I understand. So when there was previously question that we would have oxygen bleed on the anode, it was not oxygen bleed, it was oxygen coming from the cathode during a long shutdown. And that has a clear cleanup effect. And that's also like because of the sulfur oxidation.
Did you any chance investigate the effect of the membrane thickness? Because I heard earlier that the different types of MEAs were used. Did you see any effect?
Could you repeat the question?
In the first presentation, if I'm not mistaken, by Sylvie also, she showed that they used two different types of stacks, salt stacks. So I assume they had different generation of MEAs in there. Was the membrane thickness different, and could you see an effect of the oxygen crossover to the recovery from the cathode side to the anode side during this recovery step?
I think Jana can comment, but I think the MEA thickness was the same for all of the.
I think we cannot comment on that.
Okay, no problem.
Unfortunately, that's not an information that we have or can give. So this is here we come to the opening of the information about the MEAs and components and this issue. So unfortunately, the thickness is not.
No problem. Thank you very much for the clarifications.
So thanks for this question. Any further comments, feedback, question, suggestion?
Yeah, I have a question. It's addressed to Thomas, I think. Thomas Baccar. It's a bit technical, but did you show the result you get to smart chemistry regarding water concentration? Because as you mentioned that the concentration level analyzed by smart chemistry is far away than yours. So did you have a feedback from them? Have you present the results?
Yes, we shared all the results with Smart Chemistry. So they have seen everything we have done with them. We had a conversation some time ago about gas calibrant. And I believe that after sharing the result, they were looking into purchasing new water calibrant to verify their result.
Okay. Is there any new inter-laboratory comparison schedule or not with the US? Because I know there is a other lab at the US, such as Urban Labs, etc. So did you try to work with them also?
In this project, not, because it's almost finished, and we didn't have any inter-laboratory comparison planned. In another European project, so Metro IV2, we will have another inter-laboratory comparison with a synthetic fuel that will involve, or we will invite, I would say we have invited American lab to join.
Okay.
So, it will be interesting to see if they join again. As you may notice, most of these inter-comparison are anonymized. So you will have to discuss directly with each participant to know if they want to reveal you their performance.
Okay. Thanks a lot. Yeah, because I think in Metro IV2 you are working on water measurement, and I think it's a good thing because even the variability within, let's say, good laboratory, it's about 1 ppm, so almost 25% of the specification. So I think it's a good thing to work on. Perfect.
Yeah, and it's probably something that we will need to work with gas manufacturer, especially to get a reliable gas standard. I think there have been a bit of an issue in the past, so I think that will be quite good to work with you on this topic.
Yeah.
I think.
I think also.
Okay, thanks for this discussion. Any further comment? Feedback from the audience? Actually, I don't see any further comment in the chat also. Just want to give everybody the chance to give us a feedback, give us maybe recommendations. We had also a stakeholder advisory board from the industry. Some people are also there. Do you have any feedback, recommendations regarding the project results that were published today from the colleagues? Silence everywhere. Sylvie, do we have a plan if there are no further questions how to proceed? No?
No, I think we had also planned to present some conclusions by work packages, but I think that most of the reasons were really presented, unless people would like to show a slide about a general slide about your activities. Okay. What I could do, at least from my side, I can show what we did for the dissemination, communication, and so on, only on one slide. And maybe people can, by this way, have again a look to the name of the website and maybe try to join later on. Okay.
Do you want to share that?
Yes, I can try to share. Or I can just probably send the file to, yeah, it's better maybe to send the file.
Okay. If you want, you can share your screen maybe.
Okay, I can try to do that. Okay. So let's see if this works. Okay. Mm-hmm. So you can see that?
Oh yes, yes. I can see it right now.
Okay. So, well, this was a work package about dissemination, communication, exploitation, and we were responsible for this with so you, Alex, Tor, and Jana. As just I can take this opportunity to remind what we did towards the the other persons around. So first of all, we had this 3 workshops. So the presentations, the public presentations are of these workshops that were held at ZSW. Okay, no mask, everyone together. This was the first Hydrate workshop. Then we had this workshop in common with Metro IV. So it was before, it was the end of Metro IV, before Metro IV 2. Autumn 2019. And today's virtual event. So all the presentations of the first workshops public are already available on the website. The ones of today will be available on the website. So if we go to the communication aspect, this going straight here. So the website normally really gives all the public information on the project. There are some public, there's some publications, scientific publications. There were several contributions in conferences about hydrogen in general, with the World Hydrogen conferences, for example. There will be other conferences, but there will be after the project. And there was also a contribution to the technical workshop organized by Toyota and the Hydrogen Europe Association. Yes, for the conferences, we just got today that EEC 2020 now will really exist in 2022 in May. So hopefully we can present some results in Madrid of this project, as was planned to do, in fact, last year. About the interactions concerning the standards, we have strong contributions to the ISO TC 197, collaborations, participation to working groups, and also about the exploitation of our results, well, we have used the services of Horizon Results Booster. They help us with an exploitation strategy seminar. They did a report for the portfolio dissemination and exploitation strategy, and we could identify 2 main key exploitable results with online hydrogen quality sensor. This was not possible to disclose today on this. About the establishment of hydrogen quality labs and something that was presented today. So we identify reasons to be exploited at this level, but also other reasons to be exploited that will be in a report soon. And I would like to end for the hydrate colleagues on that. We have been asked to give more, communication, to do more communication actions to a wider audience, for the public, which is not so easy for us to do, but for now, we are able to prepare, and we plan to prepare a video, public video, talking about hydrate activities and hydrate partners. So that could be available to remind to all the existence of this project. And that's it for me. So thank you very much.
Thanks, Sylvia, for summing up the dissemination activities. Yeah, unfortunately, we had not the chance to meet directly, but anyhow, and for your participation here in this online conference. Still the chance to ask questions to the colleagues, technical or other stuff, if you would like to do, and take the chance. Just open your microphone and if you want, switch on your video and go ahead. So there's still no open microphone. May I assume that everything is okay for you so far? No further questions, no further comments. If there is still interest in the work that we actually performed here, you can also contact us directly by email. I think the information should be available on our homepage from the Hydrates project. We are a little bit before the planned ending. It's maybe up to me to say thank you again for all the people presented here. The main topics of this project was testing and hydrogen quality. I think we did a good job here. Hopefully, I hope that's interesting also for other people. And yeah, thanks again for joining. Thanks again for giving your feedback, comments, questions. And if there's nothing more to say, can we close before, or do we have to stay here? Yeah, I would think so.
Yes, you have to stay here.
For half an hour.
Yeah.
Quietly and calm, as in church.
I would say that for the partners that are here on the screen, if you could stay a little bit. If people cannot put their camera on, if people could put their camera on, we could maybe, if it is agreed, maybe take a picture of the screen. I don't know if Anaël could do that.
Maybe that would give us a last and final screenshot if everybody could open his video. If not, it's also okay.
If this is feasible.
Or do we crash then the internet? I don't know.
You think so? No.
I don't know. We can give it a try. Okay. I see no open video, no further microphone, no further question. Obviously, everybody is happy, and thanks again, all the participants and also the audience. And then who would like to give some closing words, Sylvia or Jana, as the coordinator.
I let you, Jana.
Thank you very much. I think the closing words were made here, but yes, thank you very much for all of you joining for today's event on my behalf also. I hope you had a nice event and learned a lot. And if any further questions, just please contact us.
Good.
Thanks
thank you
for organizing.
Thanks for organizing, Sylvie. Yes, thank you, Christian.
Thank you, Axel Match. Thank you. Goodbye.
Thank
everyone.
you also
Thank you, Anand.
from the technical committee. Work perfect. Thanks a lot.
No problem. Thank you.
Thank you.
Bye.
Thanks a lot.
Bye.
Thank you. Bye-bye.
Thank you. Thank you. Bye-bye.
Bye-bye.